The desert wind at La Flecha Farm carries dust the colour of old bone. A sheep rancher named Aurelio Hernandez is walking his land in Chubut, in southern Argentina. The year is 2014. The ground here lies cracked and pale beneath a hard, bright sky. Ahead of him, something breaks the surface of the soil, a shape, dark and curved, polished smooth by wind and grit. He stops. It is not a rock. It is the broken end of a single thigh bone. The bone is about 8 feet long. Stood upright in the dirt, it would rise taller than a grown man. You could not wrap both arms around it. Think of a fence post carved from solid stone, too thick for your fingers to meet on the far side. It has been sunk into this desert for roughly 100 million years ago, waiting, and the animal that grew it was one of the largest ever to walk the earth. Stay with that number for a moment. 100 million years. The distance is almost too wide to feel, yet here, under a rancher's boots, one bone from that lost world has come back into the light. The animal would later be named Patagotitan majorum. From the tip of its snout to the last bone in its tail, it stretched about 121 feet. That is longer than the longest blue whale ever measured, and the blue whale is the largest animal we know of anywhere in the ocean today. But the whale is held up by water. This creature carried its whole length on land, on 4 columns of living bone, under the full weight of gravity. Picture that for a second. A body longer than a whale standing in the dry Patagonian heat. Casting a shadow you could walk the length of and grow tired. Now the harder number. How much did it weigh? Here the ground gets less certain, and it is worth being honest about why. We do not have a scale from 100 million years ago. Weight is not measured from a fossil. It is estimated, reconstructed from the thickness of the limb bones and the size of the animal they had to hold up. The central published figure for Patagotitan sits near 69 or 70 tons, but the honest range runs wider than that, from roughly 50 tons at the low end to about 76 tons at the high end, depending on which method you trust. So hold the number loosely. Call it around 70 tons and remember it is a careful estimate, not a fact stamped on a bone. Even at the low end, the figure is staggering. 50 tons is heavier than a fully loaded railway car. 70 tons is heavier still, and this was not a still object. It breathed, it walked, it grew from something small into all of that. Somewhere on this same floodplain, a Patagotitan once tore mouthfuls of foliage, swallowed them almost whole, and moved on, its footfall sending a low tremor through the ground before any sound reached the air. At La Flecha, the one bone was only the beginning. When the field teams came, they did not find a single skeleton. They found a bone bed. Over several field seasons of digging, they lifted more than 200 bones from the ground, the scattered remains of at least 6 separate individuals, all resting in the same layer of ancient river sediment. 6 giants, laid down together in the floodplain of the Argentinosaurus rocks. It is one of the richest windows we have onto an animal at the very top of the size scale for anything that has ever lived on land. So that is the question this whole journey circles. How? How does a land animal get to 70 tons and keep functioning? Not by luck and not overnight. Tonight you and I are going to follow that question all the way down, from the buried bone in the Patagonian desert, back to the small, quick creatures where it all began. Stay with the thread. The size is the mystery, and the answer is stranger and more elegant than the number alone can tell you. Because here is the thing worth sitting with. In all the long history of life on land, only one lineage ever crossed this line. Only the sauropods, the long-necked plant-eaters, ever pushed a body past 30 tons and kept going again and again in different times and places. No mammal has done it. The largest land mammal that ever lived, a hornless rhino relative from Asia, may have reached 15 or 20 tons at most. That is a giant by any measure. And it is less than a third of the weight hanging on that femur in Chubut. Elephants, the largest animals walking the earth today, top out near 6 or 7 tons. Patagotitan was 10 of them. Something about the sauropods, and only the sauropods, unlocked a door that stayed shut for every other body plan on land, before and since. To understand the giant, you have to leave the giant behind for a while. You have to go back much further than 100 million years, to a time when the ancestors of these animals were not giants at all. In fact, they were small enough to hold. Travel back to the late Triassic more than 200 million years ago. The world is one connected supercontinent, dry across its vast interior, hot and seasonal. The great plant eaters of the future do not exist yet. Instead, moving through stands of ferns and low scrubby conifers, there are small, slender animals walking upright on two legs. These are the early sauropodomorphs, the root of the whole family tree. And root is the right word, because from this modest stock everything else will grow. Picture one of them clearly. It stands about waist high to you, maybe a little more. It balances on two legs, with a long tail counterweighting a fairly long neck, and small grasping hands on its shorter forelimbs. It is light, quick on its feet, able to rear up and crop leaves from heights a squat reptile could never reach. Its head is small, its teeth are simple, leaf-shaped, made for nipping and stripping foliage rather than grinding it. It weighs perhaps as much as a person or a large dog. You could imagine it startling and darting away through the undergrowth like any nervous browsing animal. Nothing about this creature announces a 70-ton descendant, and yet the seed is already there, hidden inside the bone, in a place you would never think to look. If you could slice through the leg bone of one of these early animals and hold it up to the light, you would see the first clue. The bone is not laid down the way it is in a lizard or a crocodile. Many reptiles grow in fits and starts. Their bones record it, ring after ring, like the growth rings of a tree. A season of growth, then a pause when food is short or the weather turns, then another band of growth, slow, interrupted, cautious. It is a way of building a body that keeps its options open and never commits to a fast pace. The sauropodomorphs did something different, and they did it early. Their bone tissue is dense with fine blood vessels, woven through in an open, mesh-like pattern. This is the signature of fast, continuous growth. It is bone laid down quickly and richly supplied with blood. The kind of tissue an animal builds when it is racing toward adult size and barely slowing to catch its breath. And here is the detail that matters most. The very oldest sauropods we can examine already carry this same fast-growing bone. They were not slow growers that gradually sped up over tens of millions of years. From near the very beginning, the lineage grew fast. That single fact reframes the whole tale. The machinery for getting big was not a late invention, bolted on once the animals were already large. It was there at the base in the small bipedal ancestors waiting. Accelerated growth came first. The giant bodies came later, built on top of it. When conditions allowed, the lineage could simply run that fast growth for longer and longer and reach sizes nothing else on land could touch. Think about what fast, uninterrupted growth actually means for an animal. It means a hatchling does not spend decades inching toward adulthood, exposed and vulnerable the whole way. It grows hard and grows quickly, powering through the dangerous small sizes where a predator could swallow it whole. Growth like that is expensive. It demands a steady flood of food and a body that can process that food fast enough to feed the furnace. And that requirement, that endless hunger, will shape everything else about how these animals were built. Hold on to it. It is the first of the pieces we need. Now, a moment before we go deeper, because I want you to travel this whole way with me. If you find these long walks through deep time worth taking, follow or subscribe wherever you're listening, on Spotify, on YouTube, or in your podcast app of choice. It keeps the lantern lit for the next journey. Now, back to the bone. So the growth engine was in place early. But growth alone does not explain a 70-ton animal that still worked. A body cannot simply be scaled up like a photograph. Double an animal's length, and you roughly multiply its weight 8-fold, while the bones and muscles holding it up gain far less strength for the job. Make a mouse the size of an elephant without changing anything else, and its legs would snap under it. Size is not free. Every ton you add is a problem to be solved. Bones must be arranged to bear crushing loads. Air must reach lungs deep inside a body the size of a house. Food must be gathered in enormous quantity and broken down without a mouth built for chewing. Blood must be pushed uphill against gravity to a head held far from the heart. The sauropods solved every one of these problems, not with a single trick, but with a small handful of innovations that fit together like parts of one machine. And that is the real subject of this journey. 4 solutions, each one remarkable on its own, that together carried a lineage across a size threshold no land animal has reached before or since. Let me sketch them for you now, lightly, the way you might glimpse the far peaks of a range before you set out to walk toward them. The first you have already met. Fast, relentless growth, the engine that turned a river cobble-sized hatchling into a titan within the space of a few decades. Without it, the animals would never reach giant size before old age or death caught up with them. The second is hidden in the breath. These animals did not breathe the way you do, with lungs that fill and empty like a pair of bags. They carried a system closer to a bird's, with air sacs reaching out from the lungs and pushing deep into the skeleton itself. That system did 2 things at once. It moved air through the body with astonishing efficiency, feeding the furnace of that fast growth, and it hollowed out the bones from the inside, filling them with air where a mammal would have solid weight. A honeycomb of empty chambers where you would expect dense marrow. That is how you build something enormous and keep it from crushing itself under its own frame. The third solution is the one everyone pictures when they hear the word sauropod. The neck. Absurdly, gloriously long, in some species stretching 30 feet or more from shoulder to skull. That neck was not a decoration, and, as best we can tell, not mainly a weapon or a mating display. It was a feeding tool of extraordinary efficiency. It let the animal plant its huge body in one spot and sweep a vast volume of vegetation into its mouth without taking a single wasteful step. Moving 70 tons costs energy. A neck lets you leave the body still and let the head do the travelling. And those hollow air-filled bones we just mentioned are exactly what made such a neck possible. Light enough to lift, long enough to reach. The fourth solution lives at the far end of that neck, in the head, and it is almost a trick of subtraction. The sauropod skull was small and light, with simple peg-like or pencil-like teeth, set only at the front of the jaws. There were no grinding molars. There was, as far as we can tell, almost no chewing at all. Leaves and stems went down the throat largely whole. All the hard work of breaking that food apart happened far below, in a vast gut where microbes did the digesting slowly over days in a great fermenting vat. A small head is a light head, and a light head is one you can hold at the end of a very long neck without impossible cost. Subtract the heavy chewing machinery, and the whole tower above the shoulders becomes affordable. Growth, breath, neck, and gut. 4 answers to the single question of how to be a giant on land. Over the passes ahead, we will walk into each of them slowly and see how they fit. But I want you to feel, even now, that these are not separate curiosities. They are one integrated design. The fast growth demands enormous food. The long neck gathers that food cheaply. The small head at its tip is only possible because the gut, not the mouth, does the digesting. And the air sacs feed the growth while lightening the neck that reaches the food. Pull any one piece out, and the others start to fail. Together, they open a door that stayed locked for every other creature that ever walked. And still, at the centre of it all is that first, quiet fact from the leg bone. It grew fast, and it grew without stopping. Everything else is built around keeping that furnace fed. Let me leave you tonight standing between the 2 ends of this journey, so you can feel the full stretch of what we're trying to explain. At one end is the animal beneath Aurelio Hernandez's boots at La Flecha Farm. Around 70 tons of it, give or take, with a single thigh bone 8 feet long, a fence post of fossil too thick to embrace. 121 feet from nose to tail, one of the largest living things ever to stand on solid ground, laid down in Patagonian sediment 100 million years ago. And at the other end is where every one of these giants began, not as a titan, as an egg, and then as a hatchling small enough to lift. The young of even the largest sauropods came into the world at a tiny fraction of their adult size, light enough that you could have cupped one in your 2 hands like a river cobble worn smooth by water, and felt its small weight settle against your palms. From that, in a few short decades, 70 tons. A river cobble that becomes a creature longer than a whale. That is the transformation we have to account for. Not just that the animals were huge, but that each one travelled the entire distance from your cupped hands to a shadow you grow tired walking the length of, and did it fast within a single lifetime again and again, in lineage after lineage, for well over 100 million years. Every giant in the fossil record was once small enough to hold. Every one of them ran that impossible race and won. We have found the starting line, the small bipedal browsers of the late Triassic, cropping ferns under a dry supercontinental sky, already carrying in their bones the one crucial ingredient, the fast-growing tissue that would carry their descendants across the size threshold. We have named the 4 solutions that made the crossing possible, and we have felt, I hope, the sheer scale of the gap between the hatchling and the adult. What we have not yet done is look inside the machine while it runs. To understand how a body crosses 30 tons and keeps working, you cannot stay at the level of the whole animal. You have to go down, past the skin and the muscle, into the bone itself, and watch it being built, layer by layer, faster than almost any large animal has ever built bone before. That is where the engine of size actually lives. To see how a hatchling you could hold in 2 hands became a 70-ton adult, you have to look inside the growing bone itself. To see how a hatchling you could hold in 2 hands became a 70-ton adult, you have to look inside the growing bone itself, slice a sauropod thigh bone thin enough for light to shine through it, and a hidden country appears. The bone is not the dense, solid material you might picture. It is a woven, porous tissue threaded everywhere with the ghosts of blood vessels. Researchers call it fibrolamellar bone. It is the fingerprint of an animal in a tremendous hurry to grow. Hold that thin slice to the light and look closer. The empty channels where blood once flowed are not scattered at random. In a young sauropod they line up in a repeating grid, a network so regular it looks almost engineered. Long canals run the length of the bone. Short ones cross between them, rung by rung, like the framing inside a wall. This pattern has a name. It is called plexiform, from the same root as a plexus, a braid of vessels. And that braid is the whole secret. It tells you the bone was being fed at a furious rate. Think about what a grid of blood vessels inside a bone actually means. Bone does not simply swell like a balloon. It is laid down, cell by cell, by living tissue that needs a constant supply of oxygen and raw material. The denser the plumbing, the faster the delivery, the faster the bone can grow. A dense plexiform network is the mark of tissue being poured on at a speed most living things never approach. In a young sauropod, new bone spread across the growing surface the way frost spreads across a cold window overnight, fine crystals racing outward, filling the space almost before you can watch it happen. Now compare that to the bone of a typical reptile, and you begin to see why this matters. Slice open the leg of a crocodile or a lizard, and you often find something quite different. You find rings. They look a little like the rings inside a tree trunk, and they form for a related reason. When food is short or the season turns cold, growth stalls, and the bone lays down a thin, dense line before it starts again. Paleontologists call these lines of arrested growth. Each one is a pause, a winter, a hungry stretch written permanently into the skeleton. A reptile grows in fits and starts, quickly when times are good, then not at all, then quickly again. Fibrolamellar bone tells the opposite tale. In the fastest growing sauropod tissue, those stop lines are faint or scarce, crowded out by page after page of rapid, uninterrupted growth. The animal was not waiting for a good season. It was building bone almost continuously, from the day it hatched toward the day it reached adult size, laying down that plexiform grid month after month, year after year. Growth did not stall through the lean times the way it did in a cold-blooded reptile. It simply kept going and going and going. This is the first half of the engine of size, not a single lucky gene, not one strange bone, but a growth strategy. A sauropod poured its whole life in its early years into getting big fast. And here is the detail that turns a curiosity into a genuine discovery. The very oldest sauropods, the early giants that came before the famous names, already show this same fast growth signature in their bones. The accelerated growth did not arrive late, after the animals were already huge. It came first. The speed of building bone evolved early, and the enormous size followed from it, over millions of years, as a direct consequence. That reframes the whole question. You do not ask why sauropods got big, and then wonder how they managed it. You ask why they started growing so fast. Because once an animal grows that far for that long, size is almost the inevitable result. Turn the growth rate up high enough, keep it running without a pause, and a body simply keeps expanding until other limits catch up with it. The bone histology, that landscape of braided canals in a thin slice under a microscope, is where you can actually see the decision being made. But fast growth alone leaves you with a problem, and it is a heavy one. A 70-ton animal built of solid bone would be a catastrophe. Its own skeleton would be a crushing burden. Dense, dead weight it had to drag through every step of every day. Grow that fast, get that big, and the very frame holding you up starts to work against you. There had to be a second half to the engine. There had to be a way to build something enormous that did not weigh what enormous things are supposed to weigh. And the answer is one of the strangest and most beautiful things in the whole history of life. The answer is air. Sauropods did not breathe the way you do. Your lungs are a dead end. Air flows in, oxygen crosses into the blood, and the same stale air flows back out the way it came, in and out, mixing fresh with used on every breath. A sauropod, like a bird today, almost certainly did something far more elegant. It kept a set of balloon-like air sacs threaded through its body, beyond the lungs themselves. These sacs did not do the work of gas exchange. They acted like bellows, storing and pushing air so that fresh oxygen could flow across the lung tissue in one direction, on the breath in and again on the breath out. It is a through-flow system, closer to a river than a tide, and it is one of the most efficient breathing arrangements any animal has ever owned. That efficiency alone would matter to a giant, because a giant needs oxygen delivered to a vast body. But the air sacs did something else, something you can read directly in the fossils. They did not stay politely inside the chest. They sent out fingers, thin extensions of the air sacs called diverticular, pushed outward from the lungs and crept in among the organs and then, remarkably, into the bones themselves. Where those air fingers touched a bone, they hollowed it. They ate away the solid interior and left it filled with air instead of marrow. The skeleton became in part an extension of the breathing system. You can see the result with your own eyes if you ever stand beside a real sauropod vertebra. From the outside it looks massive, a great block of bone the size of a barrel, but its surface is pitted and scooped and dimpled with deep hollows, and if you could open it you would find that much of the inside is simply not there. In place of dense bone there are thin walls and open chambers, struts and cavities, a fretwork wrapped around the empty space. In many sauropod vertebrae, fully half to 60% of the volume was air. Half the bone, or more, was nothing at all. Reach for the loaf of fresh bread on your counter, and you have the truth of it in your hands. From the outside, a good loaf looks solid and generous, a real weight. Lift it, and it is almost nothing, because inside it is a foam of thin walls around 1,000 pockets of air. A sauropod vertebra was built on that same principle. Big to look at, startlingly light to lift, and in the most extreme cases the hollowing went further still. In the long neck bones of one sauropod, the thin sheets of bone around the joints were nearly all air, something close to 9 parts in 10 empty, a whisper of mineral wrapped around almost pure space. Now put the two halves of the engine together, because separately they are clever, and together they are the reason a 30-ton land animal could exist at all. Picture what each one gives the animal, and picture them working at the same time. The air sac breathing gave the giant its oxygen. A body of that size is a furnace of living tissue, every cell of it demanding fuel, and a through-flow lung could pull oxygen from the air far more completely than your own tidal lungs ever manage. That solved the supply problem. It kept a mountain of muscle and gut and growing bone fed with the one thing it could not do without. The hollow, air-filled skeleton solved the weight problem. This is the piece that makes the whole thing possible. By replacing solid bone with the air, the animal could build a frame that was enormous in its dimensions, yet a fraction of the weight it should have carried. A vertebra could be broad and long and strong enough to bear the loads of a giant, and still weigh little more than a hollow architectural strut. Engineers reach for exactly this trick when they raise a crane over a building site. The great arm of the crane is not a solid bar of steel. It is an open lattice of thin members and empty triangles, strong where it needs to be, empty everywhere else, because a solid arm would collapse under its own weight before it lifted anything. A sauropod carried that same lattice logic inside its bones, and there is a third gift, quieter than the other two but just as important: heat. A big body has a small surface compared to its bulk, and it makes heat constantly, and it struggles to shed that heat before it cooks itself from the inside. Now thread that same body with a network of air sacs and air-filled bones, a system of internal spaces with air moving through them. You have given the animal an interior route to carry warmth away from its deep core and vent it out on the breath. The very system that lightened the skeleton and enriched the oxygen may also have helped a giant keep from overheating in the warm world it lived in. One set of structures, 3 problems solved at once. That is the engine of size. Fast, almost ceaseless growth to build the body quickly. A bird-like breathing system to fuel it, to lighten it, and to cool it. Neither one alone would have carried an animal across the size threshold. Together, over deep time, they opened a door that no land animal before or since has walked through. Before we follow that air any deeper, let me say one quiet thing, and then we will go on. If you are finding a strange comfort in the shape of these vanished lives, you can keep them close. Follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. Then settle back and let the giants keep breathing beside you. Let us stay with that breath a moment longer, because there is something almost tender about it once you understand it. The air did not merely pass through these animals, it lived inside them. It filled their bones, it pressed into the spaces around their spines and their ribs and their hips, so that a great deal of what looked like solid dinosaur, from the outside, was in truth a warm, moving cushion of air held in a cage of thin bone. To touch a living sauropod along its flank would have been to feel, faintly, the give of all that hidden air beneath the skin, the way you might feel the give of a great bellows slowly filling. And this is where a question opens that the rest of the tale has to answer. We have watched the growth, we have watched the air. We have seen how an animal could be built enormous, fed enough, lightened enough, and cooled enough to hold together at a size nothing else on land has matched. But knowing that a giant could exist is not the same as knowing what it did with that existence. An engine is only an engine. It has to drive something. The question that now stands in front of us is simple, and it is where every strange advantage we have described was pointing all along. What did the air build? Because the hollowing did not stop at a single stout vertebra in the chest. Once the breathing system had learned to invade bone, to lighten it, to fill it with living space instead of dead marrow, a whole new kind of skeleton became possible. A skeleton that could be long without being heavy. A skeleton that could reach without paying the full price of the reach. And there was one part of the sauropod body where that trick, the trick of building something huge out of almost nothing, mattered more than anywhere else. One part that every sauropod is remembered for, one part that, more than the vast body or the pillar legs or the small watchful head, made these animals unmistakable across 150 million years of the fossil record. You already know the part. You have seen it in every picture, sweeping up into the trees or out across the water, longer than any neck has any right to be. But you have probably never asked how it was possible. A neck that long, built of solid bone, would have been an impossible burden. The muscles alone could never have lifted it. The animal could never have raised its own head. The whole elegant creature would have been pinned to the ground by the weight of its most famous feature. Something had to make that neck light enough to carry, and by now you know exactly what that something was. Watch how the pieces line up. A hatchling grows fast and does not stop, so it reaches giant size in a single sustained climb. Its bones fill with air, so the giant body weighs far less than its dimensions promise, and breathes with an efficiency that keeps the whole engine fed and cool. And that same air, having learned to hollow bone, was ready to be spent on something new. Not on making the trunk a little lighter, on making a reach possible that no other design could afford. This is the moment the engine of size stops being an abstract advantage, and starts, quite literally, to change everything about the animal shape. So hold that image of the hollow vertebra, light as bread, strong as a lattice, riddled with the fingers of the breath. Hold the picture of frost-fast bone racing across a growing surface, year upon year, never quite pausing for winter. These were not separate wonders. They were one system, growth and air, working together toward a single spectacular end. In a mere geological instant, measured against the long patience of deep time, a lineage of modest, upright creatures had assembled every tool it needed to become the largest animals ever to walk the earth. And all of it now flowed toward the neck. Consider for a moment how anyone can know these things at all. You cannot set a dead giant on a scale, and you cannot stand beside it for the years it took to grow. The animal died more than 90 million years ago, and all that survives is bone turned to stone. Yet a single limb, cut and red with care, will tell you how fast it lived and roughly how much it weighed. Both answers come from the same place, the inside of the bone, and both come wrapped in honest uncertainty. Start with growth. Pick up a sauropod thigh bone, a femur as long as a tall person is high, and imagine slicing a thin wafer from its shaft. The slice must be ground down until it is almost nothing, a sheet of fossil thin enough to hold up to a lamp and see light pass through, like frosted glass. Under a microscope, that pale window fills with structure. You are looking at the record the living bone kept of itself, laid down while the animal still breathed. The work that produces that window is patient and a little ruthless. A piece of a priceless bone must be cut, set in resin, and ground away almost to vanishing, because only at that thinness will stone stop blocking the light and start revealing what lies inside it. Hold the finished section to a window, and the fossil glows, amber and grey, the ancient blood canals showing as fine, dark threads in a paler field. It is a strange intimacy, reading a giant's hurried youth in a chip you could balance on a fingertip. What you see first is the weave of the tissue. In a fast-growing animal, bone is laid down quickly and a little untidily, in a dense mesh of fibres threaded through with canals that once carried blood. Paleontologists call this fibrolamellar bone, and when its channels link up in a regular brick-like lattice, they call that pattern plexiform. It is the fingerprint of speed. Bone built this way goes down fast and almost without pause, month after month, from the moment of hatching. Compare that to a slower animal. Many reptiles do not grow at a steady pace. They surge in the warm season and stall in the lean one, and each stall leaves a mark, a thin dark ring where growth nearly stopped. These are called lines of arrested growth, and they work a little like the rings in a tree. Count them, and you begin to read a life in seasons, a slow year here, a hungry year there. Sauropod bone, for the most part, does not read that way. The fast fibrolamellar tissue runs on and on, the arrest lines faint or crowded only near the very end, where the giant finally slowed as it approached full size. The message is blunt. These animals grew hard and grew young, climbing from hatchling to many tons in a span closer to a large mammal's than a lizard's. That is the engine under all the size, and a single slice reveals it. There is more in the slice than speed alone. Where the growth does slow in those crowded final rings near the outer wall, you can begin to count, and counting gives you years. Read the spacing between the pauses and you can say, with care, roughly how old the animal was when it died, and whether it had reached full size or was still climbing toward it. A wide gap between early rings means a fast year, a season of plenty. A thin one means a hard stretch, a drought, or a lean winter, written permanently into the leg. A single bone becomes a diary, kept in tissue, closed the day the animal fell. Here is the detail that turns a curiosity into a discovery. When you take that same blade to the oldest sauropods, the early giants near the base of the family, you find the fast-growth weave already there. The plexiform mesh, the hurried tissue, the near absence of long pauses. The signature does not appear late, as a refinement added once the animals were already enormous. It is present at the start. Rapid growth came first, and the great size followed from it, lineage after lineage, as if the trick had been learned once and never given up. Now turn from how fast to how heavy, and the ground grows softer under your feet. There are two broad ways to weigh a creature you will never lift. The first is almost brutally simple. Measure the circumference of the main weight-bearing bones, the femur of the hind leg, and the humerus of the front. Add them together and feed that number into a formula built from living animals. The idea rests on something you can feel in your own legs. A limb must be thick enough to carry what stands on it, so the girth of the bone is a kind of honest signature of the load it bore in life. Thicker shaft, heavier animal. From two measurements, a body weight. The second method builds the animal back piece by piece. You take the skeleton, or a careful cast of it, and wrap it in a three-dimensional model, restoring the muscle, the gut, the lungs, the flesh that once rounded out the frame. Then you measure the volume of that reconstructed body and multiply by a plausible density, since flesh and bone weigh a little more than water while air spaces weigh almost nothing. It is slower, and it asks more of the skeleton, but it accounts for the true shape of the creature rather than trusting one bone to speak for the whole. The trouble is that the two methods do not always agree, and sometimes they disagree sharply. Scale from limb girth alone and you may get one figure. Build the volume and you may get another, lighter or heavier by many tons. Neither is simply wrong. They are asking the question in different languages, and the gap between their answers is not a failure to hide. It is the honest width of what the bones can tell you. You need not reach for the very largest to feel that spread. Take Brachiosaurus, the high-shouldered browser of the old Jurassic floodplains, known for over a century. Ask how much it weighed, and the answers still swing from around 28 tons at the light end to more than 60 at the heavy one, better than a 2-to-1 difference for a single familiar animal. The bones have not changed. The methods have, and each new way of restoring the missing flesh nudges the figure again. You can watch that width open and close across the great titanosaurs, depending on how much of each one survived. Consider Argentinosaurus, long spoken of as the heaviest of them all. For all its fame, it is known from almost nothing. A dozen or so battered back vertebrae, a piece of the hip, some ribs, and a single giant thigh bone assigned to it later. From that handful, every weight you have ever heard was reached by scaling up from more complete relatives. so the estimates spread wide, from around 60 tons at the cautious end to as much as 100 tons at the boldest. That is not sloppiness. It is what happens when you try to guess a whole tree from one fallen branch. Patagotitan sits on firmer ground, though not by as much as you might hope. At least 6 individuals came out of the same Patagonian bone bed, more than 200 bones in all, including a femur about 8 feet long. With that much to work from, the numbers tighten, yet they still range from roughly 50 tons to about 76, with a central estimate near 70. Even with 6 animals on the table, a span of 20-odd tons remains. Remember that the next time a single figure is offered as the weight of a titan. Behind the clean number stands a quiet crowd of estimates, leaning on one another. The clearest case for how completeness helps is Dreadnoughtus, pulled from southern Patagonia across 4 field seasons. Close to 70% of its skeleton was recovered, roughly 100 bones, including most of the tail in sequence. That is a rare gift among giants, and it lets the volume method work with far less guessing, since so much of the true body is actually present rather than imagined. The result, around 65 tons, is one of the better anchored weights for any animal this size. Better anchored, though, is not the same as certain. Even here, the figure rests on a model of the missing flesh, and the model carries its own margin. It helps to name the line between the two kinds of knowledge plainly. What you truly hold is the bone, its length, its girth, the weave of its tissue, the rings near its rim. All of that is direct, as solid as the fossil in your hands. The weight, the full living outline, the pace of a life measured in years, those are inference, reasoned outward from the bone into the space the animal used to fill. Good science keeps the two apart and tells you which is which. It offers a range rather than a single proud number, and it treats the width of that range as information, not embarrassment. So hold the two readings side by side, the growth and the weight, and notice that both were drawn from the same modest object, a length of fossil bone. One slice told you the animal grew fast and grew young. One girth, or one restored volume, told you it weighed as much as a small herd of elephants, give or take a margin you were honest enough to keep. And when you look one last time into that thin, light-holding wafer, you notice something the growth lines nearly distracted you from. The bone is not solid. It is threaded and chambered, hollowed by cavities that in life held no marrow at all. That same invasion of air, pushing deep into the skeleton, was about to reshape the one part of the body that would define these animals forever, the neck. That invasion of air did not stop at the lungs. It kept pushing outward along the spine, hollowing the bones of the neck one chamber at a time, and that single fact, air where solid bone should be, is the quiet secret behind the most recognizable shape in all of natural history. Stand for a moment in a late Jurassic clearing, roughly 150 million years ago, in the country we now call the Morrison Formation. Conifers rise in dense stands around you, araucarias and podocarps, with cycads and tree ferns filling the shade below. There is no grass here, there are no flowers, and moving through that green and resinous world is a neck longer than anything a land animal has grown before or since. You're watching an engineering solution walk across a floodplain. That is the honest way to see it. Before you follow the science, let me ask one small thing of you. If these slow giants settle something in you, follow along, and let the quiet hours keep coming. Now look closely at that neck, because everything depends on what is inside it. A mammal builds its bones dense and heavy, packed with marrow. A sauropod did the opposite. Its neck vertebrae were invaded by soft outpocketings from the lungs and air sacs, thin sleeves of tissue that burrowed into the bone and scooped it hollow. What remained was a lattice of thin struts wrapped around open, air-filled chambers. In many sauropods, half the volume of a neck vertebra, sometimes closer to 60%, was simply air. Hold that number in your mind because it changes what a long neck actually costs. Length is cheap only if it is light. A solid bony neck grows heavier faster than it grows longer, and at some point the animal cannot hold its own head up. But if you replace bone and marrow with air as you extend, the penalty softens. The neck can keep reaching out across the clearing while weight it adds stays modest. Air did not just fill the neck. Air is what permitted the neck to exist at all. In one extreme case, the hollowing went almost absurdly far. A sauropod named Sauroposeidon from the early Cretaceous of what is now Oklahoma is known from 4 neck vertebrae found still linked in sequence. In parts of those bones, in the thin projecting rami near the joints, the airspace reached roughly 89% of the volume, nearly 9 parts air to 1 part bone. The living structure there was closer to a stiffened membrane than to anything you would call a skeleton. Reach out and imagine lifting one of those bones. You brace for the mass of something a yard across, and instead it comes up light, almost weightless in your hands, like a bundle of dry reeds bound together into a hollow column. That is the tactile truth of a sauropod neck. Not a heavy beam of bone, but a stiff, airy scaffold. Closer in principle to the hollow struts of a crane boom than to the dense, marrow-filled limb bone of a horse or an elephant. From those 4 vertebrae, paleontologists estimated the whole neck of Sauroposeidon at around 37 to 39 feet. Think about that distance on the ground. It is longer than a school bus, held out from a single set of shoulders, and yet built to be as light as the animal could possibly make it. Every added foot of reach was bought not with heavier bone but with more enclosed air, so the neck could be long and it could be light. The next question is the one that matters most. Why grow it at all? What did all that reach actually buy an animal in the plain currency of survival, which is food, and the energy it costs to get it? Here the answer is beautifully simple, and it comes down to a phrase worth sitting with. Feeding envelope. Picture the sauropod standing still, its 4 legs planted like columns in the soft floodplain silt. Now picture the volume of vegetation its mouth can reach without those legs moving at all. Up into the conifer canopy, down to the ferns at its feet, and side to side sweeping through a wide arc as the neck turns. That entire reachable volume of leaves and shoots is the feeding envelope, and the long neck makes it enormous. Watch what the animal is not doing, because that is the real saving. It is not walking. A body of 30, 40, 50 tons is monstrously expensive to move even a short distance. Every step means lifting and swinging pillars of muscle and bone, and every step costs energy that has to come back out of the food. A short-necked browser has to relocate its whole body to reach the next mouthful. The long-necked sauropod does not. It stands in one place and lets the neck do the travelling. That is the elegant idea proposed by Michael Taylor, Matthew Weedle, and Darren Naish, and laid out plainly in a 2013 paper with a title that says it all, on why sauropods had long necks. The neck is a way to harvest a large volume of plants while paying almost nothing to move the body. It is cheaper in raw energy to sweep a light neck through the leaves than to march several tons of animal from tree to tree. Reach, not travel. That is the trade. Feel the difference in your own body. Imagine standing at the center of a wide table crowded with food, your feet fixed to the floor. If your arm were long enough to sweep across the entire table without a single step, you would eat far more for far less effort than a person forced to walk a slow lap around it for every bite. The sauropod neck is that impossibly long arm, and the 4 planted legs are the fixed feet that make the reach worthwhile. This is why the 4-legged stance matters so much to the story, and why it is not a side detail. A sauropod stood on 4 columnar limbs, weight spread across a broad, stable base. That stance is what freed the neck to become a tool. Anchored on a wide, motionless platform, the neck could swing out and sweep through a long arc, brushing across the canopy the way a slow, harvesting arm passes over a field, while the great trunk behind it barely shifted at all. The body became the base, and the neck became the working limb. You can almost hear how quiet that feeding was, A mammal grazing fills the air with the steady grind of molars, jaw sliding side to side, crushing every mouthful before it goes down. A sauropod made almost none of that sound. There was the tearing and stripping of foliage, the soft rake of teeth pulling a branch bare, and then the swallow. Where you expect chewing, there is a strange silence. The eating was mostly harvest and gulp, a long, slow stripping of the trees and little more. That silence is a clue to the whole design, and it leads straight to the animal's head. Because the head is the other half of why the neck could be so long. Look at it, and you might be surprised by how small it is. On a body the size of a house, the skull of a sauropod was often no larger than a horse's, sometimes smaller. Light, short, and simple. And that smallness was not a flaw. It was a requirement. Think about what sits at the very end of that 30-something foot neck. Whatever weight rides out there, the animal has to hold up all day against gravity at the far end of the longest lever in its body. Put a heavy, muscular, grinding head out there, and the neck must be thicker and stronger just to carry it, which makes it heavier, which shortens the reach it can afford. A light head is what keeps a long neck cheap to hold. The two features are locked together. Small skull and long neck evolved as partners, each making the other possible. So the sauropod gave up the heavy machinery of chewing entirely. Its teeth were not broad grinding surfaces. In many groups they were narrow and peg-like, or slender and pencil-shaped, and crowded toward the front of the mouth. They were not tools for processing food. They were tools for gathering it, for raking and stripping leaves and shoots off the branch. The teeth cut the plant free from the tree, and then the plant went down the throat essentially whole and unchewed. That raises an obvious problem, and it is worth being honest that early ideas about it turned out to be wrong. If the mouth does no chewing, something else must break the food down. For a long time, one popular answer was a gastric mill, a churning gut full of swallowed stones that ground the leaves the way a bird's gizzard does. It is a tidy picture. It also does not hold up. When researchers actually weighed the stomach stones found with sauropods and compared them to what a working gizzard needs, the stones came up far too rare and far too small. Gastroliths turn up with only about 4% of sauropod skeletons, and in those cases the amount is nowhere near enough to mill tons of foliage. There was no grinding stomach. What there was instead was time, and heat, and microbes. A sauropod broke down its food the slow way, through fermentation in a vast hindgut, a long internal chamber where colonies of bacteria did the chemical work that teeth and stones did not. The plant sat and warmed and rotted into usable energy inside the animal over hours and hours. The body itself was the food processor, a giant fermentation vat on 4 legs, quietly digesting the forest it had swept up. For a long time, this was strong inference rather than something anyone had watched directly, read off the shape of the teeth and the absence of a gizzard. Then a remarkable fossil closed part of the gap. In a sauropod closely related to Diamantinosaurus, from Australia, paleontologists recovered actual preserved gut contents, fossilized remains of a last meal. Inside were leaves and stems, swallowed largely whole and unchewed, exactly as the tooth and jaw evidence had predicted. The animal cropped its food and gulped it down intact and let the gut do everything else. Rare direct confirmation of a feeding strategy long read only from bones. Step back and see how tightly all of this fits together, because the pieces are not separate facts. They are one solution. The head is small so the neck can be long. The teeth only crop so the head can stay small. The chewing is gone, so the gut must ferment, which favours a huge body to hold that slow fermentation, and the huge body is expensive to move, which is exactly why the long neck, the reach without walking, pays off so handsomely. Pull any one thread and the others answer. It is a single interlocking economy of eating, and the neck sits at the heart of it. Now there is an older and more romantic idea about that neck, and it deserves a fair hearing before we set it aside. Look at a modern giraffe, and you will find male giraffes swinging their necks like clubs, slamming their heads into rivals in contest over mates. From that, some researchers wondered whether the sauropod neck grew long for the same reason, as a weapon of combat or a banner of sexual display, a structure shaped by competition for mates rather than by the search for food. It is a genuine hypothesis, and it was tested seriously in a 2011 study led by Michael Taylor and colleagues that looked hard at the evidence, and the reasoned conclusion, offered as the better supported reading rather than as absolute proof, ran the other way. The sexual display idea struggles to explain the pattern. When a feature evolves mainly to win mates, it usually differs sharply between males and females, and it tends to appear strongly only in one sex at maturity. Sauropod necks do not read that way. Long necks show up broadly across these animals, in a manner that fits a feeding tool far better than a courtship ornament. The weight of the reasoning favours the plainer answer. The neck is, first and foremost, about food. That does not mean the neck was never used in display or in disputes. Almost any large, striking body part can end up recruited into a threat or a show, and a 40-foot neck reared over a rival would be a genuinely imposing sight. But used for and evolved for are different claims, and the honest position is a careful one. The dominant force shaping that neck, the pressure that made it grow generation after generation, was the simple economics of reaching more leaves for less effort. Display, if it happened, rode along on a structure built for the harvest. Keep that economy in view as you look across the late Jurassic world these animals lived in, because it explains something striking about them. The Morrison Formation was not home to one giant sauropod. It held at least a dozen different species living side by side, the richest gathering of sauropods known anywhere in the fossil record, and necks were a large part of how they shared the land without starving each other out. Consider Brachiosaurus, moving through those same conifer stands. Unlike most sauropods, its front legs were longer than its back legs, tilting the whole body up at the shoulders into a steep giraffe-like posture. That build lifted its neck and head high, letting it browse in the upper canopy, among branches that lower-shouldered sauropods sharing the floodplain simply could not reach. One animal fed high in the trees, others swept low across the ferns and horsetails. The feeding envelope was not just large, it could be tuned, angled up or down by the shape of the limbs and the set of the neck, so that many giants could partition one forest between them. That is the deeper meaning of the long neck. It was not only a way to eat more, it was a way for enormous animals to coexist, each carving out its own slice of the vertical world, from the ferns at ground level to the resinous crowns of the taller conifers. A dozen kinds of sauropod in one landscape, each with a slightly different reach, is what a well-designed harvesting arm makes possible. And it was, in the end, a harvesting arm. Return once more to the animal standing still in the clearing, feet planted in the drying mud of a seasonal floodplain, the ground beneath it cracked from a long dry spell. The great body does not move, only the neck travels, swinging slowly through its wide arc, the small head at its tip raking leaves from one tree, then the next, without a single step being taken. Sweep, strip, swallow, sweep, strip, swallow. Tons of animal fed by a light air-filled arm reaching out across the trees, patient and unhurried, hour after hour in the Jurassic heat. You're looking at the most efficient large plant harvester the land has ever produced. Light where it needed to be light, long where length paid, and small-headed where a heavier head would have ruined the whole arrangement. A body built around the simple, relentless logic of reaching food without carrying itself to it. Everything about the neck, the air inside the bone, the reeds-like vertebrae, the tiny cropping head, the vanished chewing, points back to that one idea. But that same reach created a problem the animal could not solve with air and light bone alone. It is one thing to hold a neck 40 feet long, it is another thing entirely to keep it alive out there cell by cell to the very tip. And that leads us out of the quiet economy of feeding and into the harder physics of the blood. In the floodplains of the American West, roughly 155 to 145 million years ago, a shape moved through the conifers that you could not fit inside any room you know. This was Brachiosaurus altithorax, and it was built wrong in the most useful way. Its front legs were longer than its back legs. Most four-legged giants keep the shoulders low and the hips high. Brachiosaurus reversed the plan. That one choice tilted the whole animal upward. The spine climbed from tail to shoulder, and the neck rose off that raised platform like a ramp continuing into the sky. You have seen the same trick in a giraffe, though at a scale no giraffe could ever reach. Stand beside it, and your eyes would find only leg. The shoulder alone carried the base of the neck to a height you would call the third floor of a building. From there the head kept climbing. Brachiosaurus ran somewhere between 66 and 85 feet from nose to tail. Its weight is harder to pin down, and honest science admits it. Depending on the method, the estimates spread from about 28 tons to as much as 62 tons, a range wide enough to hold two very different animals inside one name. That uncertainty is not sloppiness. It is what happens when you try to weigh a creature from bones alone, guessing at the muscle and the air that once filled the gaps between them. What the fossils do show clearly is posture. The long forelimbs and the steep chest gave Brachiosaurus a reach that its neighbours simply did not have. In the Morrison Formation, more than a dozen kinds of sauropods shared the same seasonal woodland, the richest gathering of these animals known anywhere. Most of them cropped the low and middle greenery, the ferns, the horsetails, the softer fronds near the ground. Brachiosaurus reached over their heads. It fed high in the Araucarian and podocarp canopy, in a layer of needles and cones that shorter shoulders could never touch. No grass grew there. No flowers had yet evolved. The high larder was resinous, tough, and almost entirely its own. You can thank a patient man in Colorado for the name. In the year 1900, a partial skeleton came out of the rock in the western United States, and a paleontologist named Elmer Riggs studied it. 3 years later, in 1903, he described it and called it Brachiosaurus altithorax, the deep-chested arm lizard. That holotype still rests at the Field Museum in Chicago, a scattering of bones that founded the whole idea of the tall, browsing giant. From those few pieces, generations of readers learned to imagine the animal looming over the Jurassic like a living derrick. But here you meet a tangle worth untying slowly, because it has fooled careful people for decades. For much of the 20th century, the most complete and most famous brachiosaur skeleton in the world did not come from Colorado at all. It came from Tanzania, from the late Jurassic beds of East Africa. That mounted giant, the one that towered inside a museum hall and set the popular image of Brachiosaurus for generations, was long filed as an African species of the same genus. It is now recognized as a separate animal with its own name, Giraffatitan, the giant giraffe. The split matters more than a label. It means that many of the boldest old numbers printed under the word Brachiosaurus were never measuring the Colorado animal. They were measuring Giraffatitan. When you read some vintage claim about the height or the weight of Brachiosaurus, you may be reading a description of the African cousin instead. The two were close relatives, alike in their tall-shouldered plan, but they were not the same creature. Untangling which bone belongs to which name is quiet, slow work, and it keeps changing the picture of both. Even together, though, these Jurassic browsers were not the end of the line. The tall neck design carried on into the next period, into the early Cretaceous, and there it produced a neck that reached higher than anything the Morrison ever grew. The animal is called Sauroposeidon proteles, and it came out of the ground in Oklahoma, in the coastal plain sediments of the Antlers Formation, laid down roughly 110 to 100 million years ago. Sauroposeidon is known from almost nothing, and that nothing is astonishing. What survived is 4 neck bones, 4 cervical vertebrae, still lined up in the order they held in life. From those 4 pieces alone, the neck is estimated at about 37 to 39 feet long. Hold that in your mind against the room you're in. The neck by itself was longer than most living rooms are wide, longer than a school bus. A single limb of an animal stretched out across the floor of your imagination like a fallen mast, and the bones themselves were enormous in one dimension, while nearly weightless in another. A single one of those neck vertebrae laid on the ground would run longer than a canoe. You could not lift it, yet the living animal held a whole chain of them aloft and swung it gently through the treetops. That is the paradox that makes Sauroposeidon such a prize. A bone that big should be far too heavy to raise on the end of a 40-foot lever. It was not, and the reason is hidden inside the bone. Cut one of these vertebrae across if you could, and you would not find the dense, marrow-filled core of a mammal's leg bone. You would find air. Sauropod neck bones were riddled with hollow chambers, pockets that connected to the lungs and to a system of air sacs threaded through the body, the same bird-like breathing machinery that living birds still carry. Those pockets replace solid bone with empty space. Across many sauropods, the neck vertebrae ran roughly half to 60% air by volume. In Sauroposeidon, the trick reached an extreme that still seems barely believable. In parts of its neck bones, in the thin struts near the joints where the vertebrae link together, the airspace reached about 89% of the volume. Read that number again slowly. Nearly 9 parts in 10 of that bone were emptiness. What remained was a lattice of paper-thin walls, a scaffold arranged with the economy of a crane boom rather than the solidity of a limb. The engineering is the same. You do not build a tall reaching arm out of solid metal. You build it out of thin struts and open triangles strung along the lines of stress and hollow everywhere else. Evolution found that answer long before any bridge did, and it wrote the answer into living bone. This is the quiet secret behind every one of these towers of neck. The height was not paid for in dead weight. A solid neck of that length would have been impossible to lift, a burden that no muscle at the shoulder could have swung upright. The air-filled neck weighed a fraction of what its size suggests. It let Brachiosaurus keep its head in the canopy without exhausting itself, and it let Sauroposeidon push the design further still, out to a reach that flirts with the physical limits of what a spine can do. So picture the whole shape once more, standing in the Cretaceous morning with its head somewhere near 40 feet in the air. The shoulders raise the base of the neck to the 3rd floor window. The neck itself, light as a hollow spar, lifts the small head higher again, up past the level where any rival could feed, into the still air above the forest. Below, the ground carries the animal's weight through columns of leg. Above, the head drifts among the topmost needles, cropping and stripping, barely moving the vast body it belongs to. It is a machine tuned for one purpose, to hold a mouth in the sky and keep it there cheaply, and it worked. For tens of millions of years, across 2 continents and 2 geologic periods, these tall browsers reached where nothing else could reach. The bones tell you how they built the height. The air inside the bones tells you how they kept the height liftable. Every part of the puzzle you can hold in your hand seems for a moment solved. The neck rises, light and long, into the warm Cretaceous air. But a neck that long forced a harder question, the one every giant heart in Patagonia had to answer. How do you lift blood 40 feet into the air? But a neck that long forced a harder question, the one every giant heart in Patagonia had to answer. How do you lift blood 40 feet into the air? Hold that problem for a moment. First, watch the animal simply stand. A titanosaur at rest is a study in columns. Each leg is a pillar of bone stacked almost straight beneath the body. The thigh bone alone can run 8 feet, thick as a fallen trunk. This is graviportal design, the architecture of an animal built to carry crushing weight. Nothing about it is built for speed. Everything about it is built to not collapse. You have seen this shape before, in miniature, in the leg of an elephant. But scale that elephant up past 60 tons and the rules tighten. Muscle and tendon can only pull so hard against gravity. So the skeleton takes over the work and the limbs move toward vertical. There, bone carries the load with almost no muscular effort. A sauropod does not so much hold itself up. It balances quietly on 4 living props. Now watch it walk. The motion begins somewhere deep in the shoulder, slow and deliberate. One forelimb unlocks, swings and reaches ahead. There is no bounce in it, no spring. The foot floats forward like a heavy door swinging slowly shut, and then it lands. Only then does the weight transfer, pouring from one column into the next. A single footfall can take a full second, or more, to complete. That slowness is not laziness. It is physics. A limb this massive cannot be flung. It must be lifted, carried, and set down with care, because a stumble at this scale can shatter bone. So the giant moves at a walk it almost never breaks, a pace measured in the long, even rhythm of a tide. And here is a detail you would feel before you understood it. Stand a short way ahead of a walking titanosaur, and the first thing to reach you is not sound. It is the ground itself. Each footfall drives a low tremor through the soil, a pressure wave that travels faster through packed earth than through open air. The vibration arrives in the soles of your feet a heartbeat, before any noise finds your ears. You feel the giant coming before you hear it. We know these gaits partly because sauropods left their walking behind, pressed into mud that hardened into stone. The richest record of all sits above what is now the Bolivian city of Sucre, on a great limestone wall called Calorco. Once it was flat. A coastal mudflat, soft and level, drying and flooding with the seasons. Then the Andes rose, and the whole surface tilted with the mountains, until today it stands nearly upright, canted to about 72 degrees. That single slab holds more than 12,000 individual footprints. They cross and recross in roughly 465 separate trackways, a tangle of comings and goings frozen in place. Theropods walked here. So did armoured plant-eaters, and among them, again and again, the broad round craters of sauropod feet, each print sunk deep by an animal weighing tens of tons. One trackway stands apart from all the others. It belongs to a young sauropod, a juvenile, and it runs on and on across the ancient mud. Follow it, and it does not quit. It stretches for nearly a third of a mile, close to 1,600 feet of unbroken, patient steps. It is the longest single dinosaur trackway anyone has ever traced. You can read the stride in it, the calm and even spacing of a growing giant crossing a flat and open world. Stand at the base of that tilted wall and let the scale settle on you. Every one of those prints was a moment, a foot lifted and set down, a full second of a life. 12,000 moments, preserved because the mud was soft enough to take the mark and gentle enough when the sediment returned to keep it. The whole surface is a single afternoon of deep time, held upright against the sky. But a body this large is not only a problem of standing and walking, it is a furnace that must be fed. And here the sauropod did something that still seems impossible when you first hear it. It grew to the size of a house, and it never once chewed its food. Look inside that small head, high on the end of the neck. The teeth are simple pegs, or thin pencils, crowded at the front of the jaws. There are no broad grinding surfaces, no molars, nothing built to mash a mouthful into pulp. These teeth do one job. They strip. They rake through a branch of conifer or a stand of ferns, comb the foliage free, and pass it back to be swallowed nearly whole. The mouth is a harvesting tool, not a mill, so picture the sound of a sauropod feeding and notice what is missing. A herd of mammals grinds as it grazes, a steady wet churn of jaws working side to side. Here there is none of that. Only the tear and rasp of leaves being pulled from stems, then the long silence of swallowing. A giant eats in near quiet, hour after hour, while its jaws do almost nothing at all. For a long time, one explanation for this seemed obvious. Perhaps the animal ground its food deep inside instead, using a gizzard packed with swallowed stones. Birds do this. So do crocodiles. Stones churning in a muscular stomach can crush plant matter as thoroughly as any tooth. It was a tidy idea, and it had a name, a gastric mill, but the stones do not support it. Swallowed stomach stones turn up with only about 4 sauropod skeletons in every 100, and where they do appear, they are too few and too small to have done the work. Measure the mass of grit a bird carries to grind its food, scale it to a body of many tons, and the sauropod comes up far short. The stones that were found are polished and modest, more likely swallowed by accident with a mouthful of plants than gathered on purpose to crush them. There was no mill in there. So how does an animal digest a forest without chewing it? The answer was never in the mouth, it was in the gut. A sauropod ran on fermentation. Deep inside that vast body lay an enormous hindgut, a warm and churning vat where microbes did the breaking down. Bacteria, not teeth, unlocked the tough cellulose of conifer needles and fern fronds. The animal only had to swallow and wait, and let the sheer size of its interior buy the time. This is the quiet advantage of being enormous. A larger body holds a larger gut, and food can sit inside it longer. The longer it sits, the more completely the microbes strip every last calorie from material that would starve a smaller animal. Size did not just make the sauropod impressive, size made its whole way of eating possible. The giant and its gut grew together. For decades this was inference, read from teeth and jaws and the geometry of the belly. Then, in much later rock in what is now Australia, one relative of the titanosaurs died with its last meal still inside it, and the stone kept it. When it was opened, there were the leaves and the stems, swallowed largely whole and barely broken. No grinding, no pulp, just plant matter gulped down intact, left for the body to dissolve from within. The strategy that had only been imagined was suddenly there in front of you, preserved. Think of what that gut freed the animal to do. A grazing mammal is chained to its molars, forced to spend hours chewing before it can swallow. A sauropod skipped that entire step. It could crop and crop and crop again, filling the vat as fast as its neck could sweep. The small head on the long neck made sense now in a new way. It did not need to be large. It was only a mouth on the end of an arm, and the real work happened far below. Which brings us back at last to the hardest problem of all. Not walking, not eating, circulation. Because a body this tall with a head lifted so far above the heart runs straight into a wall of simple physics. Blood has weight. To push it upward is to fight gravity every inch of the way, and the taller the climb, the harder the fight. In your own body, the distance from heart to brain is small, and the pressure needed to bridge it is modest. Now raise the brain. Raise it the height of a 4-story building above the heart that feeds it. Every beat must shove a column of blood up that entire climb and keep pushing, or the head goes dark. Consider the tallest necks the sauropods ever grew. In the early Cretaceous of what is now Oklahoma, around 110 million years ago, an animal called Sauroposeidon carried a neck near 37 feet long. 4 of its neck bones survive, and they are among the longest ever found in any creature. Held upright, that neck would lift a head some 40 feet into the air, higher than almost anything alive has ever raised its skull. To feed a brain at that height, the heart faces a brutal arithmetic. Look at a modern giraffe, the tallest animal walking the earth today. Its head rides only a fraction as high, yet its heart already labours under enormous strain. The average pressure in a giraffe's arteries runs near 214 millimeters of mercury, roughly double your own. That is the cost of lifting blood just a few extra feet against gravity. Now scale that pressure up to a sauropod's height. Run the numbers, and a heart working like a giraffe's, only larger, could push blood to a head no more than about 40 feet above it, before the demand becomes impossible. The vessels would need walls too thick, the muscle too vast, the pressure too extreme for any tissue to bear. 40 feet is not a random figure. It is close to a hard ceiling, a physiological wall built into the physics of a beating heart. And the tallest sauropod stood right against that wall. Sauroposeidon, with its head near 40 feet up, was living at the very limit of what a single heart can do. There was almost no room left above it. Grow the neck taller, and no heart of flesh could keep the brain supplied. The giants had not just grown large, They had grown as tall as the laws of circulation would allow. Sit with that for a breath. The size of these animals was not open-ended. It was fenced in on every side by rules they could not break. Bone set one limit, the gut set another, and the beating heart drew a hard line in the air, a height beyond which blood simply would not go. But there is a catch in this arithmetic, and honesty demands we name it. All of it assumes the animal held its neck high, raised up near vertical, brain far above heart. And that assumption is not settled. It is one of the real, live arguments in the study of these creatures. Perhaps the tallest sauropods did not habitually crane their necks skyward at all. Perhaps they held them lower, closer to level, sweeping side to side across the ground and the low canopy, rather than reaching for the treetops. A neck held horizontal changes the whole equation. If the head rides near the height of the heart, the terrible pressures ease, and the cardiovascular wall retreats. The animal that looked trapped against a ceiling may simply have carried its head where the climb was gentler. Others have wondered whether the heart had help. Extra pumping stations, smaller auxiliary hearts spaced along the neck, sharing the lift the way relay pumps push water uphill in stages. Or some clever trick of the plumbing, a siphon effect, where blood falling down one side of the loop helps draw blood up the other, easing the burden on the heart itself. Each idea has its defenders. None of them has been proven. The soft tissue that would settle the question rotted away 100 million years ago and left no trace. So we are left with the bones and the physics, and an honest uncertainty between them. We know the necks were long. We know the physics of lifting blood is unforgiving. What we do not yet know is exactly how these animals held their heads, and so exactly how close to the edge each one truly lived. That question stays open, and we will return to it, because posture sits at the heart of what these giants were. For now, hold the whole animal in your mind at once. The columned legs that move like slow doors, each footfall a full second, each step a tremor that outruns its own sound. The stripping teeth and the silent churning gut that digested a forest without a single chew, and the great heart at the centre, pushing blood up a 4-story climb, straining against a ceiling written into physics itself. Every part of it was a compromise with limits. Nothing about a sauropod was excessive by accident. Each was as large as it could be, and no larger, held in shape by the quiet arithmetic of bone and blood and gut. To be a giant was to live inside a narrow band of the possible, pressed against every wall at once. Stand for a moment on a floodplain that vanished long ago, roughly 150 million years ago. The air is warm and faintly dry. It carries a scent you would know at once if you let it settle on the back of your tongue. Resin, crushed needle. The clean, sharp sting of conifer sap, sharp enough to taste, like a fistful of pine needles brewed slowly in your palm. This is the western interior of the land that will one day be called North America. You're standing inside the Morrison, the richest sauropod country the world has ever held. The ground beneath your feet tells a seasonal story before you look up. In one place it is cracked hardpan, pale clay split into plates by months without rain. A few steps on it turns soft and dark, silt left behind when a river spilled its banks. This was a warm, seasonal, semi-arid world, closer to a savanna than to any deep, dripping jungle. Long dry spells broke open into short, violent rains. Herds moved with the water, and the water moved with the year. To the east, the land is quietly emptying of sea. For ages, a broad, shallow ocean, the western interior seaway, had reached up across the continent. Now, across the long, slow stages the geologists call the Kimmeridgian and the Tithonian, it is withdrawing northward, draining off the low country and leaving behind broad plains laced with river channels. Where saltwater once stood, floodplain now spreads flat to the horizon. Braided rivers wander across it, splitting and rejoining, dropping sandbars, carving shallow banks. It is on these river margins that the giants gather. Now look up, and let the scale of the place arrive. Overhead the canopy closes like a green ceiling, held up on the straight trunks of Araucarian and podocarp conifers. These are stiff, resinous trees, kin to the monkey puzzle and the podocarps that still cling on in the southern world today. Their branches interlock high above, filtering the light into a soft, moving green. Walk beneath them and the temperature drops. The resin smell thickens. You feel small in the way you feel small inside a cathedral, except this ceiling is alive, and it is food. Below that high roof, the understory fills in the rest of the world. Cycads squat in thick clusters, their crowns of stiff fronds fanning out at waist height and shoulder height. Beside them stand the Benetitalians, a vanished group that looked much like cycads but were something else entirely, now gone from the earth without descendants. Ginkgos spread their fan-shaped leaves along the wetter ground. Tree ferns arch overhead in the damp hollows, and in the marshy edges horsetails grow in dense green stands, jointed and hollow, rising from the mud like bundles of thin reeds. Here is what you will not find, no matter how far you walk. There is no grass, not a single blade. Grass has not yet evolved, and it will not spread across the world for tens of millions of years more. There are no flowers either, no bright petals, no blossom, no fruit, no scent of nectar on the wind. The flowering plants have barely begun, and they do not yet rule anything, so the whole living pantry of this world is built from conifer, cycad, fern, ginkgo, and horsetail. Every giant here eats gymnosperm and fern, and nothing else, because nothing else exists to eat. That single fact shapes everything you're about to see. This is not a soft green meadow you could lie down in. It is a landscape of needle and frond, of tough, fibrous, resin-heavy foliage, brown and green and stiff. To live here on plants alone, a body has to solve a hard problem. The food is everywhere, but it is low in reward and slow to break down. The answer the sauropods found was not to eat better food, it was to eat enormous amounts of poor food, and to grow a body big enough to make that work. And so they came, in a variety seen nowhere else in the fossil record. At least a dozen different sauropod species are known to have shared this one ecosystem, the most diverse gathering of these animals ever found anywhere on Earth. Think of what that means standing here. Not one kind of giant, but 12 or more moving across the same floodplains, drinking from the same channels, feeding in the same forests. In most of the world, one giant grazer crowds out the rest. Here, a dozen coexisted. The question is how so many titans divided a single pantry between them without starving one another out. The answer is written in their necks and their shoulders, and you can read it by looking at the height of their heads. Among them moves Brachiosaurus, a creature built unlike its neighbours. Its front legs are longer than its back legs, so its shoulders rise steeply and its neck sweeps upward, giving it a posture much like a giraffe scaled to monstrous size. That build lifts its small head high into the conifer canopy, into green ceiling that no shorter animal in the whole assemblage could reach. It feeds where the light is, stripping needles from branches 30 and 40 feet above the churned mud, in a layer of the forest all its own. Beneath that high browser, the others take the middle and the low country. The long whip-tailed diplodocids, animals like Diplodocus and the enormous Apatosaurus, carry their necks lower and more level. They sweep those necks in wide arcs from a nearly stationary body, mowing the understory, raking in horsetails and low fern and cycad frond across a broad reach without taking a single step. A neck like that is a harvesting arm. It lets a 40-ton animal clear an entire patch of ground while its columnar legs stay planted, saving the vast cost of hauling that body from meal to meal. Divide the forest into floors, high and middle and low, and suddenly a dozen giants can share one plain in peace. Now listen, because the sound of this place is the strangest thing about it. A herd of giants is feeding all around you, and yet there is almost no sound of eating. You hear the tear and rasp of foliage as peg-like teeth strip needles and fronds from the stems. You hear the soft crash of a branch bending and releasing, and then nothing. No grinding, no chewing, no slow, sideways working of jaws that you would hear from any herd of grazing mammals. These animals do not chew at all. Their small heads carry only simple, pencil-shaped teeth at the front of the mouth, good for stripping and gathering, useless for grinding. The food goes down whole. That silence is the sound of a different machine at work, hidden deep inside the body. Where a cow or a horse would grind its meal to pulp between broad molars, the sauropod simply swallows the vegetation and lets its gut do the labour. Inside that enormous trunk sits a vast fermentation chamber, a warm vat where microbes break down the tough plant fibres over days, releasing their energy slowly. The animal is less a browser and more a walking cauldron, and its great size is partly just the room it needs to hold that cauldron. Stomach stones turn up with only a small fraction of sauropod skeletons, too few and too slight to have served as a mill. The grinding was never in the mouth. It was in the microbes and in time. So you begin to feel the shape of this world as a whole. The heat lies heavy across the open plains. The rivers wander and shift, drying to strings of pools in the long season, then swelling brown and fast when the rains come down. Along their green corridors the conifer forests rise, and beneath the green ceiling the giants move in their separate feeding floors, tearing and swallowing in near silence, converting a landscape of resin and frond into tons of living flesh. When the dry months bite, the herds follow the retreating water across cracked clay, and where they walk, the ground itself carries their weight before any sound of them reaches you. It is a world of hard limits gently kept. The food is poor, so the body must be huge. The head must stay small and light at the end of a long neck, so it cannot chew, so the gut must do the work instead. Grow fast, stay simple in the mouth, ferment slowly in the belly, and divide the forest by height so that many giants may share one plain. Every animal on this Morrison floodplain lived by that same quiet arithmetic, and so did every sauropod that came before them, and every one that would come after, in every warm valley on every shifting continent. The needles change, and the rivers change, and the names of the giants change. The arithmetic does not. Hold in your mind the problem of the raised head, and the long climb the blood must make to reach it. Picture Sauroposeidon, a slender browser of the early Cretaceous coastal plains. Its neck was built from hollow vertebrae stacked into a column near 40 feet long. About 110 million years ago, that neck lifted a small skull into the conifer canopy of what is now Oklahoma, and for every moment it stayed up there, the heart far below had to drive blood against the pull of the whole world. Think of the height plainly. A head held near 40 feet above the heart sits at the top of a tall standing column of blood. To keep the brain fed, the heart must hold a mean pressure somewhere on the order of 178 to 236 millimeters of mercury. That is not a comfortable figure. It sits right at the estimated ceiling for any land animal that has ever drawn breath. Push much past it, and the vessels meant to contain that pressure begin to fail. So the tallest sauropods were not simply impressive. They were operating at the very limit of what a circulatory system can bear. How did they manage it? Here the fossil record goes quiet and careful people disagree. Bone can be measured. Blood pressure cannot be dug from stone. So what follows is a set of competing ideas, each honest, none yet proven, each trying to explain the same stubborn number. Begin with the simplest picture. One heart, enormous, doing all the work alone. This is the giraffe answer, scaled up past reason. A living giraffe already runs one of the highest blood pressures in the animal world, a mean near 214 millimeters of mercury, roughly double your own. It pays for that with a thick, muscular left ventricle and tight vessel walls that keep its legs from swelling. Now imagine a heart asked to do far more. To feed a head 40 feet up, a single sauropod pump would need to be vast, a slab of muscle you might picture as a full wheelbarrow load of meat, contracting slowly hour after hour against that towering column. It is possible, but the cost is steep. Such a heart would burn a great share of the animal's energy, simply keeping the brain from starving, and the pressure it generated would strain every artery in the neck. That strain is what drives the second idea. If one heart at extreme pressure seems reckless, why not share the burden? So some have proposed auxiliary hearts, smaller muscular pumps spaced along the neck itself, each lifting the blood a stage higher, like a chain of workers passing a heavy load hand to hand up a ladder. In this picture, no single pump faces the full column. Each handles only its own short stretch, at a gentler pressure, and the head is fed by relay. It is an elegant thought. It solves the pressure problem cleanly, and there is no fossil trace of it at all. No vertebrate alive carries booster hearts strung along its neck, and soft tissue like that leaves nothing behind in rock. The idea survives because it is possible to imagine, not because anyone has found it. Treat it as a hypothesis wearing borrowed plausibility, no more. The third idea steps back from the plumbing and questions the pose. What if the head was rarely 40 feet up at all? What if the neck spent most of its long life held low and forward, sweeping across ferns and low growth rather than reaching for the canopy? Lower the head, and the whole problem shrinks. The column of blood is shorter. The pressure the heart must beat becomes ordinary, and no exotic organ is required. A predominantly horizontal neck turns a physiological crisis into a quiet routine. This is not a trivial claim. The feeding advantage of a long neck comes partly from staying still while the head does the reaching, and much of that reach is sideways, not skyward. So a habitually low posture would ease the heart and still earn its keep at the dinner table. Which brings us to the honest crack running under all of this. We do not actually know how sauropods held their necks in life. The debate over posture is real and unresolved. Some reconstructions raise the neck near vertical, swan-like, into the treetops. Others keep it low and level, a long horizontal boom sweeping the understory. The bones permit a range, and the muscles and cartilage that once fixed the true habit are gone. This is why the cardiovascular question cannot be settled on its own. The pressure a sauropod needed depends entirely on where it carried its head, and that is precisely the thing we cannot yet pin down. Solve the posture, and you narrow the models. Leave the posture open, and every model stays on the table. Now the fourth idea, the strangest and the most seductive. It is the siphon. Picture water standing in a very tall drinking straw. Once the straw is full, the weight of the liquid falling down one side helps pull liquid up the other, and you no longer have to lift the entire column by force. Apply that to the neck. Blood rising through the arteries toward the head, and blood draining back through the veins, might form a closed loop where the descending side offsets the ascending side. If so, the heart would only need to overcome friction inside the vessels, not the full dead weight of 40 vertical feet of blood. The ceiling drops. The giant heart is no longer required. It is a beautiful piece of physics, and it may not survive contact with a living body. A siphon works cleanly in a rigid pipe. Blood vessels are not rigid. Under very low pressure at the top of a tall loop, thin-walled vessels tend to collapse, pinching shut exactly where the siphon most needs them open. So the drinking straw that works on a countertop may not work inside a neck of soft, pulsing tissue. The siphon idea is offered, and it is genuinely contested, and no one has confirmed it operated in any dinosaur. Keep it where it belongs, as a possibility argued over, not a fact established. So line them up, one giant heart, straining at the ceiling, a chain of smaller hearts, sharing the climb, a low-slung neck, dodging the problem altogether, a siphon, borrowing gravity to help. Notice that they are not all rivals in the same way. The posture idea and the siphon idea both try to lower the pressure the animal ever faced. The single heart and the relay hearts both try to supply whatever pressure was truly needed. An animal could even have blended them, a strong heart and a mostly level neck working together, reaching high only in brief bouts when a particular tree was worth the effort and the risk. That last thought matters because it reminds you the ceiling was not a wall the animal slammed into once. It was a tax paid continuously. Every time a sauropod chose to lift its head, it spent circulation it could have spent elsewhere. Every foot of extra reach cost pressure, and pressure cost muscle, and muscle cost food. A neck that could touch the highest boughs was not simply a gift. It was an expensive tool, used with a caution written into the vessels themselves. We will likely never watch it happen. Soft tissue rarely fossilizes, and a beating heart least of all. So this is one of those places where paleontology reaches the edge of what bone can tell and admits the boundary out loud. What we have is a measured height, a calculated pressure sitting right at the physiological limit, and a handful of competing solutions, each partial, each unconfirmed. The tallest necks known, Sauroposeidon among them, sit closest to that edge, which is exactly why they draw the argument. For now, the honest answer is that we do not know which solution the giants used, or whether they leaned on more than one at once. What we can say is that the height of a sauropod's head was never a free choice. It was a negotiation with gravity and pressure, settled vessel by vessel, valve by valve, in a body pushed to the outer limit of what blood can climb. These were the rules that bound every sauropod, and along the rivers of Cretaceous Patagonia, one group of titanosaurs pressed them to the very edge of what a body can be. These were the rules that bound every sauropod, and along the rivers of Cretaceous Patagonia, one group of titanosaurs pressed them to the very edge of what a body can be. These were the rules that bound every sauropod, and along the rivers of Cretaceous Patagonia, one group of titanosaurs pressed them to the very edge of what a body can be. These were the rules that bound every sauropod, and along the rivers of Cretaceous Patagonia, one group of titanosaurs pressed them to the very edge of what a body can be. Picture a warm inland basin, roughly 101 million years ago, where seasonal rivers braided across a wide floodplain. The ground is a patchwork underfoot. In places the mud has dried and cracked into hard plates that clink like broken pottery. Elsewhere the last flood left silt soft enough to swallow a footprint whole. Across this country moves an animal so large that the earth reports its coming before any sound reaches you. You feel the tremor first, a slow pulse rising through the soles of your feet. Then the shape resolves against the haze, grey and unhurried, a long neck sweeping the far bank the way a crane arm swings a load. This is Patagotitan majorum. It is among the largest animals ever to stand on dry land. Let that scale settle into your body for a moment, because the numbers only mean something once you have felt the ground shake. From nose to tail tip, this animal stretched roughly 121 feet. That is longer than 4 school buses parked bumper to bumper, laid across the floodplain in a single living line. A central estimate places its weight near 69 or 70 tons. Think of that as the mass of 10 large bull elephants gathered into one body, balanced on 4 columnar legs. And those legs were built for the burden. A single thigh bone, one femur, measured about 8 feet long. Stand it upright, and it would rise past your head like a doorway turned into bone. Lay it on its side and you could sit on it as you would a fallen log, your feet swinging clear of the ground. You should know that a figure like 70 tons is not a thing anyone weighed. No scale on earth ever held this animal. The weight comes from the bones, from the thickness of the limbs and the circumference of the shafts that carried the load, fed into scaling models that translate structure into mass. Different methods pull the answer in different directions. Published estimates for Patagotitan have ranged from around 50 tons at the light end to 76 tons at the heavy end. So hold the number gently. 70 tons is the middle of a considered range, not a line stamped on a certificate. That honesty matters here, because with the very largest sauropods, the size you hear quoted often rests on a surprisingly small pile of bone. Patagotitan is a happy exception to that rule, and the way it came to light is worth walking through slowly. The first clue surfaced on a sheep ranch in Chubut province, in the dry heart of Argentine Patagonia. A worker noticed a great shape breaking the surface of the desert soil, a bone longer than a grown man is tall, weathering out of the ground where the wind had scoured the sediment away. Word reached the Museo Paleontologico Egidio Ferruglio, the institution most people simply call the MEF, based in the town of Trelew. What followed was not a single lucky dig, but a campaign. Over 7 expeditions across several field seasons, the crews returned again and again to the same bone bed, and the ground kept giving. By the end, they had recovered more than 200 bones. The material did not come from one skeleton, but from at least 6 individual animals. Their remains mingled in the same layer of ancient floodplain. That abundance is the quiet miracle of the site. Most giant sauropods are known from scraps, a vertebra here, a limb bone there, and the rest reconstructed by inference. Patagotitan gave paleontologists overlapping parts from several bodies, which let them cross-check one bone against another and build a far steady picture of the whole. When you see this animal reconstructed, you're looking at something unusually well grounded in real recovered material, not a hopeful sketch stretched over a few fragments. The most famous version of that reconstruction stands far from Patagonia, cast in fiberglass and mounted for the public. When it was installed, the skeleton proved too long for the hall meant to hold it. Its neck and head could not be contained within the gallery walls, so the mount was arranged with the head and neck reaching out past the doorway, stretching toward the corridor beyond, so that visitors met the animal's face before they had fully entered the room. Consider what that means as a physical fact. A building designed to display dinosaurs could not fit this dinosaur inside a single room. The animal overflows the architecture built to contain it. Now let the floodplain shift. Move a few million years forward and a short distance across the basin into the beds of the Huincul Formation near Plaza Huincul in Neuquén province. The world here is much the same, a semi-arid inland plain cut by seasonal channels, baked hard in the dry months and drowned in the wet. Roughly 96 to 92 million years ago, this ground carried an animal whose name has become a byword for sheer bulk, Argentinosaurus huinculensis. For decades it has worn the crown of largest known dinosaur in the popular imagination, and yet the truth of it is stranger and more humbling than the fame suggests. The discovery began, as so many great finds do, by accident and misreading. In the late 1980s, a farmer working his land near the town came upon a massive object protruding from the rock. At first glance it looked like a piece of petrified wood, a fossil log of the kind that litters these ancient floodplains. It was in fact bone, part of the leg of one of the heaviest animals ever to walk the earth. The specimen was reported to the local museum, the Museo Carmen Funes, and a team led by the Argentine paleontologist José Bonaparte began excavation at the end of the decade. In 1993, Bonaparte and his colleague Rodolfo Correa formally described the animal and gave it its name. Here is the part that should make you sit with the uncertainty. For all its fame, Argentinosaurus is known from remarkably little. The original material amounts to about a dozen incomplete back vertebrae, part of the sacrum where the spine fuses over the hips, a scattering of ribs, and a single limb bone referred to the genus. That is nearly the whole of it. There is no skull, no neck, no articulated skeleton laid out in the rock. It is one of the most incomplete animals ever to hold a record for size. Every length you have ever heard for Argentinosaurus, every weight, is an extrapolation. Nobody has measured this animal from end to end, because most of its length has never been found. So when you read that Argentinosaurus stretched somewhere between 98 and 131 feet, and weighed anywhere from 60 to 100 tons, understand what those numbers are. They are the output of scaling, of taking the few real bones and comparing them against the proportions of more complete relatives, then projecting the missing pieces. Change the relative you scale from, or the method you use, and the answer moves by tens of feet and tens of tons. Most researchers favour the lower and middle parts of that range rather than the extreme upper end. But the honest position is a wide band of possibility, not a single confident figure. The animal is genuinely enormous. It is also genuinely mysterious, and the two facts live together. That single referred thigh bone deserves a pause of its own, because it remains one of the largest limb bones ever assigned to any dinosaur. Stand beside where such a bone lay in the rock and the human scale simply drops away. This was a load-bearing column, a pillar of the living bone that carried a share of 60 tons or more with every step, through mud that grabbed at the foot and dry clay that jarred it. And remember the setting. These were not lush jungles. The Hinkle Plain went through long dry intervals broken by seasonal rains, so a herd of animals this size would have had to track greenbrows across a landscape that swung between parched and flooded within a single year. To be that large in a country that starved and drowned by turns is its own kind of achievement. If you are listening to this drift by in the dark, let the shapes keep moving. There is one more titan to meet, and it is the one that lets us speak with the most confidence of all. Travel south now, far south, into Santa Cruz province near the tip of the continent, into the beds of the Cerro Fortaleza Formation. The time is roughly 77 million years ago, later in the Cretaceous than the two giants we have just left. The animal here is Dreadnoughtus shrani, a name chosen to mean something close to fears nothing, after the great armoured warships whose sheer mass made them all but untouchable. For a sauropod of this size, it is a fitting name in more ways than one. Dreadnoughtus was excavated over 4 field seasons in southern Patagonia, in a campaign led by the American paleontologist Kenneth Lacavara. What the team pulled from a single bone bed changed how well we can know an animal this large. They recovered roughly 100 identifiable bones, adding up to about 70% of the skeleton, leaving aside the skull. That completeness is extraordinary for a giant titanosaur. Most are known from a handful of elements. Dreadnoughtus came out of the ground with most of its tail vertebrae still in sequence, along with a claw and toe bones and much of the rest of the body. At the time it was described, it was the most complete giant titanosaur skeleton anyone had ever found. Because so much of the animal survived, its size rests on far firmer ground than the figures for Argentinosaurus. Dreadnoughtus measured about 85 feet long and is estimated to have weighed near 65 tons. Notice that it is shorter than Patagotitan and lighter than the highest guesses for Argentinosaurus, yet its weight is the one we can trust most, because it was calculated from a real, largely present skeleton, rather than projected across a void of missing bone. That is the quiet lesson these three animals teach together. The most famous giant is the least known. The record holder in the headlines is the one built from the fewest bones. And a slightly smaller animal, more patiently recovered, gives us the steadiest measurement of what a 60-ton body truly was. Even so, that 65-ton figure carries its own honest margin. It comes from volumetric and scaling models, from wrapping estimated flesh and air around the recovered bones and reckoning the whole. Completeness narrows the error, it does not erase it. This is worth remembering every time a single number is offered for an animal that no living person has ever seen breathe. We are always reading the past through the arithmetic of what remains. One bone from Dreadnoughtus tells the story of these titans in miniature, or rather in the opposite of miniature. Among the recovered material was a neck vertebra with a central body more than 3 feet across. Try to hold that in your mind as a physical space rather than a measurement. This is a single bone from the middle of the neck, and it is wide enough that you could curl up inside its hollows and hollow arches like a traveller sheltering in a small stone archway. That is not a flourish. Sauropod neck vertebrae were riddled with air spaces, honeycombed with chambers connected to the lungs, so that the living bone was closer to the light, hollow struts of a crane boom than to the dense marrow-filled bone of your own arm. The size is real, and the emptiness inside it is real, and both Hawaiian animal could grow a neck like this without being crushed by the weight of carrying it. There was one more gift in that Patagonian bone bed, small and singular. Among all those 100 bones, the team found a single tooth. No skull was preserved, so this one worn peg is the only direct trace of how Dreadnoughtus fed. A lone survivor of the mouth that stripped tons of vegetation from the Cretaceous plain. Everything else about its feeding we must infer from relatives, from the shape of titanosaur jaws and the wear on other teeth. But the tooth itself is real, recovered, a fragment of the working edge of a 65-ton life. So which of these was the largest? You have probably been waiting for the answer, and the honest reply is that there is no settled one. The title of largest sauropod, and therefore largest land animal ever, is genuinely unresolved, and it shifts with every new discovery and every reanalysis of old bones. At various times the crown has been placed on Argentinosaurus, on Patagotitan, on a fragmentary giant called Puertosaurus known from a mere handful of enormous vertebrae, and on Notocolossus, championed by others in turn. Each has had its moment. None has held the title beyond dispute. When most of a record-breaking animal is missing, the ranking is only ever as firm as the next expedition, and the next expedition keeps arriving. This is not a failure of the science. It is the science working exactly as it should, refusing to pretend to a certainty the bones cannot support. A body at the far edge of what is physically possible leaves fossils that are hard to find, hard to complete, and hard to measure, precisely because the animal was so rare and so vast that a whole skeleton almost never comes to rest in one place. The uncertainty is not a gap in the story, it is the shape of the story, honest to the fragmentary record these giants left behind. In the long reach of deep time, even a creature this immense passes as little more than a geological instant, a few scattered bones pressed into a few thin layers of rock. Set the rankings aside, then, and return to the plane itself, because that is where the meaning lives. Whatever the exact order, these titanosaurs of Patagonia represent the outer limit of a body plan, tested across more than 100 million years of sauropod evolution. They are the answer to a question the whole lineage had been asking since the Triassic. How large can a land animal become before its own bones, its own heart, its own gut can carry it no further? Patagotitan, Argentinosaurus and Dreadnoughtus stand near that ceiling, each in its own slice of Cretaceous time, each on its own stretch of the same drying, flooding Patagonian floodplain. Stand once more in that landscape and let your senses fill it in. The air is warm and dry, carrying the resin scent of conifers and the mineral smell of cracked mud. Somewhere a seasonal river still runs, narrow and brown between wide banks. A footfall lands nearby, and the sound arrives late after the ground has already told you. Each footprint bites deep into the soft silt, sharp-edged and broad, deep enough that a smaller animal could shelter in the hollow it leaves. The stride is so long and so slow that a single step seems to take a full second to complete, the raised foot hanging for a moment before it comes down and the whole basin trembles again. Nothing about this animal is quick. Everything about it is vast. You will not hear it chewing. That silence is one of the strangest details of the scene. These giants stripped foliage with peg-like teeth and swallowed it nearly whole, with almost no oral processing at all, so the sound of feeding was tearing and stripping and swallowing rather than the steady grinding a herd of mammals would make. Where you expect the busy noise of jaws, there is instead a great quiet, broken only by the rip of branches and the slow shift of enormous feet. A 60-ton animal moving through its world, feeding as it goes, almost soundless except for the tearing and the tread. Feel the full weight of the achievement one last time before we follow these animals into the next part of their lives. A neck vertebra you could shelter inside like a stone archway. A thigh bone as tall as a doorway when you stand it on end, long enough to sit upon like a bench when it lies on its side. 6 individuals mingled in a single Patagonian bone bed, more than 200 bones lifted out over 7 patient expeditions, a skeleton too long for the hall built to hold it. These are not exaggerations dreamed up to impress you. They are the plain measurements of real animals that walked real ground at the outermost edge of what flesh and bone have ever managed on this planet. Picture a dry hillside in the province of Neuquén in the south of Argentina. The year is 1987. A farmer named Guillermo Heredia is crossing his land, a stretch of scrub called Las Overas, when something in the ground stops him. A shape breaks the surface of the soil. It is long and pale and hard as stone, because that is very nearly what it has become. At first he takes it for a fallen log, an old trunk turned to rock over unimaginable time. You would likely have thought the same. Petrified wood is common in this weathered country, and the thing has the grain and heft of old timber, but it is not wood, it is bone. What Heredia has found, half swallowed by the dry earth, is a single leg bone from an animal so large the mind has trouble holding it. Paleontologists now believe that first piece was a fibula, one of the 2 slender bones of the lower leg. Think about that for a moment. Not a thigh bone, not a spine, not some central pillar of the skeleton, a calf bone, and even that lesser bone was long enough and thick enough to pass for a fallen tree in a farmer's field. The bone made its slow way to the Museo Carmen Funes in the nearby oil town of Plaza Huincul. And there the real work began, the patient, unhurried labour that turns a curiosity in the dirt into a named creature. In 1989, a team led by the Argentine paleontologist José Bonaparte came to the site to dig. This is the part the world rarely sees. Not a single dramatic moment, but seasons of kneeling in the heat, brushing grain by grain, chasing the edges of something enormous through the rock. What they lifted from the ground was, in truth, very little of the animal. Roughly a dozen incomplete back vertebrae. Part of the fused hip, the sacrum, some ribs, and that great leg bone. From this scatter, and almost nothing else, they were looking at one of the largest creatures ever to stand on land. Each backbone alone was the size of a person, a barrel of stone you could not wrap your arms around. Set them in a line and you begin to feel the length of the trunk that once carried them. In 1993, Bonaparte and his colleague Rodolfo Coria described the animal formally and gave it a name, Argentinosaurus huinculensis, the giant of Argentina from Huincul. It was, and remains, one of the most famous dinosaurs in the world, and here is the quiet paradox at the centre of its fame. This creature, so often crowned the largest land animal that ever lived, is known from a handful of broken bones. You could lay everything anyone has ever found of it across a modest room floor. That is why you should be careful with the numbers. You will hear that Argentinosaurus stretched perhaps 100 feet, that it weighed as much as a herd of elephants. Those figures are honest estimates, but they are estimates. They come from scaling up the proportions of better-known relatives, from taking a fragment and asking what whole animal it implies. Change the method, and the size shifts. The truth is that no one has ever seen a complete Argentinosaurus, in bone or in flesh. It is a giant reconstructed from its own shadow. Then, in 1996, the site gave up one more prize. A thigh bone, a femur, later referred to the same great animal. It is still one of the largest single limb bones ever assigned to any dinosaur. A column of fossil you would strain to lift, taller than a person standing. Today, it lies on public display in that same museum in Plaza Huincul, and people come to stand beside it. You put your hand near it and feel the strange arithmetic. 1 bone, 1 leg, and from that, a body you cannot fully picture. This is the detective work of paleontology, and it rarely offers the whole skeleton. It offers a piece and a question and years. So consider what it means when a giant is found nearly whole. Move now to the far south of the same country, to Santa Cruz province in windswept southern Patagonia. The rock here is the Sauroposeidon Formation, laid down some 77 million years ago, when this was a warm floodplain threaded with rivers. Beginning in the year 2005, an American paleontologist named Kenneth Lacovara and his team came to a single bone bed in this cold, empty country. They would return for 4 field seasons through 2009, digging when the weather allowed and covering the excavation when it did not. What they found changed the arithmetic entirely, not a scatter of fragments, but roughly 100 bones from a single titanic animal. Most of the tail, its vertebrae still lying in sequence, one behind the next, the way they sat in life. A claw. Toes. Enough of the skeleton, some 70% of it apart from the skull, to make it the most complete giant of its kind ever unearthed. After Argentinosaurus and its ghostly handful of bones, here at last was a titan you could measure rather than merely guess at. They named it in 2014 Dreadnoughtus shrani. The genus name is worth sitting with. It means, roughly, fears nothing. A grown animal of this size, some 85 feet from nose to tail tip, and weighing perhaps 65 tons, would have had no predator on Earth that could reasonably threaten it. The name is a claim about a life, drawn from the confidence of the bones, and the bones are staggering to stand beside. A single vertebra from the neck has a core wider than 3 feet across, wider than the span of your open arms. Yet if you could look inside it, you would not find solid stone. You would find a honeycomb of hollows, chambers that in life held air, a structure closer to the light lattice work of a crane than to the dense marrow bone of a horse or a whale. The animal built itself enormous and kept itself in part empty. For all its completeness, one thing was almost entirely missing: the head. No skull came out of that Patagonian ground, which is the common fate of sauropods, whose tiny skulls sat loosely on their long necks and were lost easily to scavengers and rivers. But amid the great postcranial bones, the team recovered a single tooth. One tooth. It is the only direct evidence of how this creature fed, a narrow peg built for stripping foliage rather than chewing it. From that one small survivor, you can begin to read the diet of a 60-ton animal. Think about the physical labour behind these discoveries, because it is easy to forget. A bone this size cannot simply be lifted from the earth. It is fragile, cracked through by ages of pressure. So the workers wrap it. They coat the exposed fossil in wet plaster and burlap, building a hard white shell around it, a field jacket, before undercutting the rock beneath and rolling the whole mass free. A single jacket around a giant limb bone can weigh as much as several sacks of wet sand, dead weight that must be hauled across open country by hand and by machine. Some blocks take a full season simply to prepare for the journey, and then comes the longest part, the part with no drama at all, the waiting. Between the moment a bone breaks the surface and the moment the animal receives its name, years pass. For Argentinosaurus, the first bone surfaced in 1987, and the formal name came in 1993. 6 years, for a fibula mistaken for firewood to become the most famous giant in the world. For Dreadnoughtus, 4 seasons of digging, and then years more of cleaning, measuring, comparing, before the description could be published. In the laboratory, the plaster is opened like an egg, and the slow removal of stone from bone can take longer than the removal of bone from the ground. This is how the giants come to us, not whole, not sudden, but recovered piece by piece from the places where they fell and were buried. A farmer mistakes a leg for a log. A crew in Patagonia lifts a tail one bone at a time. A single tooth stands in for a mouth no one will ever find, and out of all this patience, out of plaster and dust and careful argument, the scale of these animals slowly comes clear, larger than anything that has walked the land before or since. But size on this order is never a private thing. An animal weighing tens of tons does not simply exist in a landscape. It presses on it, shapes it, feeds a whole world of smaller lives around and beneath it. The evidence of that pressure survives too, in forms far stranger than a single buried bone. A body that large left its mark not only in stone, but in the nests it scraped into the floodplain and the hunters that moved along its trail. A body that large left its mark not only in stone, but in the nests it scraped into the floodplain and the hunters that moved along its trail. A body that large left its mark not only in stone, but in the nests it scraped into the floodplain and the hunters that moved along its trail. Come south with me now, into the red badlands of Neuquén, in what is today Argentina. Roughly 80 million years ago, this ground was a broad seasonal floodplain, warm and half dry. Rivers crossed it through the wet months, then shrank back into cracked and dusty channels, and onto one low open stretch of that plain the giants came to lay. The place carries a name now, Auca Mahuevo. In 1997, fossil hunters working these beds found eggs, not a single clutch, and not a dozen, hundreds of them, spread across the old floodplain surface, whole groups of eggs, set close together, preserved almost exactly where the animals had left them. It is one of the richest windows we will ever have into how the largest land animals began their lives. Picture the ground as it looked then, a flat, open expanse of silt and drying mud stretching out under a pale sky. Along it, low mounds and shallow scrapes dug close to one another. This was not one nest. It was a nesting field, spread wide as a shoreline of scraped hollows, and into each of those hollows a titanosaur had laid a clutch of eggs. You can hold the size of those eggs in your mind easily. They were subspherical, close to round, averaging about 5 inches long and 4.5 inches across, not much larger than a big grapefruit. That is a striking thing to sit with. The mother might have weighed 30 or 40 tons, taller at the hip than a house. And yet each egg she laid was small enough to rest in your two-cupped hands. The shells tell you more than their size. Under close inspection, each shell surface is textured with tiny raised bumps, a single node ornamentation covering the outside like fine gravel pressed into clay. Those nodes were not decoration. They helped the porous shell breathe, letting the developing embryo take in oxygen and shed moisture through the buried nest. Every egg was a small sealed lung, waiting in the warm ground. The nests themselves survived too, and that is rarer still. The titanosaurs at Auca Mahuevo did not build tall structures. Each female scraped a shallow pit into the soft floodplain sediment, a rimmed hollow perhaps a few feet across. Into some of these pits plant debris was layered in, dead leaves and stems that would rot and warm the clutch, the way heat rises from a compost heap. Then the eggs were laid and covered and left. The mother moved on. What came next belonged to the ground and the sun. Now walk your eye across the whole surface, clutch after clutch laid close together, packed across the floodplain like cobbles on a beach. This was a colony. Many females returning to the same low ground in the same season, choosing the same soft, well-drained sediment to bury their eggs. And the deposits reveal something even more patient than that. The egg layers appear at more than one level in the rock stacked through the sediment. That means the giants came back. Season after season, perhaps year after year, the herd returned to this same stretch of plain to nest again over the buried remains of nests that had come before. That is site fidelity, and it is a behaviour we can read directly from the layered rock, not merely guess at. The animals trusted this ground. Something about it, the drainage, the sun, the safety of open sight lines, drew them back across generations. You're standing, in your mind, in a place these animals chose on purpose, again and again, across a span of time longer than most species last. And inside a few of those buried eggs, the most delicate treasure of all was waiting. Embryos, unhatched titanosaurs, so young they never took a breath of Cretaceous air, preserved within their shells. In the best of them, you can make out identifiable features of the tiny skull, the shape of a jaw, the sockets where teeth were forming. These are the youngest giants we have ever found. Curled inside a shell you could cover with one palm lay the beginning of an animal that, had it lived, might have grown longer than a tennis court. Hold those two scales together for a moment, the hatchling and the adult. A newborn titanosaur was small enough to be snatched by almost any predator on that floodplain, small enough to shelter beneath a fern. Its parent could not have protected it even if it tried, because a foot that could crush the nest was no shield against the small and the quick. From that fragile beginning, the animal would have to grow thousands of times its hatching weight, crossing nearly the entire size range of land life on its way up. Most did not make it. The numbers demanded that most would not. This is the quiet heart of how the giants worked, and it runs against everything your instincts might expect. Think of the largest mammals alive, the elephants and the great whales. They invest enormous care in very few young. One calf at a time, carried for a year or more, defended fiercely, taught for years. The bigger the mammal, the fewer offspring it tends to make, and the more each one costs. If a titanosaur had bred like an elephant, the arithmetic would have collapsed. A 30-ton animal simply cannot raise a 30-ton calf the way an elephant raises a small one. So the giants did the opposite. They flooded the ground with eggs, many offspring per season, each one small, each one cheap, each one left to the odds. It is the strategy of the fish and the sea turtle, scaled onto the body of the largest creatures ever to walk the land. Lay dozens of grapefruit-sized eggs, bury them, move on, let the floodplain sort the survivors. The few that lived would grow fast and grow enormous, and they would only need to breed a handful of times across a long life to keep the population steady. That single trick may be the deepest reason giants could exist at all. A landscape can only hold so much weight. A herd of 100-ton animals must be spread thin, a few individuals across many square miles, because the plants can feed no more than that. Thin populations of huge animals are fragile by nature. But by producing many small young instead of a few costly ones, the titanosaurs could keep replacing themselves even at very low density. The nests at Auca Mahuevo are the visible proof of an invisible bargain. Small eggs in great number were the price of adult bodies without limit. If you follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice, this slow walk through deep time will find you again. Now, let us stay a while longer on that floodplain because the nesting ground was never a safe place. It only looked calm. Cross the same basin, out of the nesting fields, and you find the other side of life at giant scale, the predators. In these same Patagonian rocks, only a little older and a little younger than the nests, lived some of the largest meat-eating dinosaurs ever discovered. They were not tyrant dinosaurs of the northern kind. They belonged to a different line, the cardiovascular, named for teeth like the blades of a shark, and two of them, in particular, stalked this landscape. One was Giganotosaurus, a hunter that rivaled the greatest predators of any age in sheer length. The other was its close relative Mapusaurus. Both carried skulls built long and narrow, jaws lined with flattened blade-like teeth. Those teeth were not the thick, bone-crushing spikes of a tyrannosaur. They were edged like serrated knives shaped to slice. A single bite from such a mouth did not need to crush. It only needed to open a long wound and let it bleed. Against an animal too large to kill in one stroke, that was the sensible design. You do not overpower a mountain, you wound it, and you wait. And here the fossil record hands us one of its most tantalizing and most debated scenes. At a site called Canadon del Gato in New Ken, paleontologists uncovered a bone bed of Mapusaurus. Not one skeleton, but many jumbled together in a single deposit. When the bones were sorted, they came from a minimum of 7 to 9 individuals, and they were of different ages and sizes. Small ones, large ones, mingled in the same grave of rock. Several giant predators, of one kind, buried together in one place. That discovery lit a question that is still burning. Why were so many of these great hunters in one spot? The most exciting reading is that they lived and hunted together. A pack of Cardiodontosaurids, adults and youngsters, cooperating to bring down prey no single one of them could manage alone. Picture that for a moment. A titanosaur the size of a small ship, and around it a coordinated group of blade-toothed hunters, working the flanks, opening wounds, wearing the giant down over hours. It is a scene that has filled documentaries and paintings, and it may be true, but you should hold it loosely because the honest answer is that we do not yet know. A bone bed is a place where bodies gathered, and bodies gather for more reasons than friendship. A drought can strand many animals at a single shrinking waterhole, where they die together and are buried together. A flood can sweep carcasses into one bend of a river. A poisoned pool, a mud trap, a season of famine, any of these can pile the dead of one species into a single deposit without those animals ever having cooperated in life. The Maposaurus bone bed is strong evidence that these giants tolerated one another and aggregated at least sometimes. Whether they hunted as a true pack, with tactics and shared purpose, remains an open and actively argued question, not a settled fact. That distinction matters, and I want to be plain about it. The animals were real, the bone bed is real, the count of 7 to 9 is measured from the bones themselves. What we build on top of that, the coordinated hunt, the strategy, the social life, is inference. Careful inference, worth taking seriously, but inference all the same. The rock records the death. It does not always record the reason. A good look at deep time means learning to feel the difference between the two, and to sit calmly with what we cannot yet decide. Set the predators back into the wider scene though, and one thing is clear enough. To be a titanosaur on this floodplain was to live every stage of life under different rules. As a hatchling out of one of those grapefruit eggs, you were prey to almost everything. A mouthful for a lizard, a small dinosaur, a wading crocodile relative at the water's edge. Through your fast-growing youth, you climbed out of one danger zone into another. Too big for small hunters, still not too big for the great ones. Only at full size, at many tens of tons, did the killing largely stop, because by then no predator could reasonably bring you down alone. Size was not just about reaching food, size was armor. Size was the thing that finally bought an adult its peace, and yet even that peace had a price, and it leads us to the last hard question. If gigantism worked so well, if the long neck and the fast growth and the many small legs all fit together so neatly, why are there no titanosaurs on the floodplain today? Why did the giants end? Part of the answer lies in the very fragility we have been circling. A population of enormous animals is by necessity a small population. The land can carry only so many 100-ton bodies. Spread that thin, a species has little margin. There is no vast reserve of individuals to absorb a run of bad luck. A herd that takes decades to raise each animal to breeding size cannot bounce back quickly from a collapse. Populations this thin can fade away without a single dramatic event, worn down by ordinary pressures that a smaller, faster breeding animal would shrug off. Layer the environment on top of that. This was a seasonal world, swinging between flood and drought within a single year. Greenbrows came and went across the landscape, and the herds had to track it moving with the water. In a good stretch, the plains fed the giants easily. But the rains were going to fail again, as they always did, and a long enough dry spell could empty a floodplain of everything that grew. A single bad season did not change everything. The giants were built to weather one hard year, but bad seasons that stacked, drought upon drought, or a slow shift in climate and vegetation across many thousands of years, could pull the ground out from under a population already living at the edge of what the land could hold. We can see, in the broadest strokes, that the giant titanosaurs did decline. Through the later Cretaceous, the greatest of them grow rarer in the rock. The colossal nesting colonies, the herds of 100-ton browsers, thin out toward the close of the age. Exactly why, in each case, is where evidence gives way to careful reasoning. We cannot stand on that ancient floodplain and watch it happen. We can only read what the layers preserved, the last high beds where giant bones appear, and above them the silence where they do not. And this is where honesty must hold the line against a good story. It is tempting to name one clean cause, one villain, one moment. The truth is quieter and less certain. The end of the giants was almost surely many pressures at once, braided together over long spans of time, shifting climates, changing plant communities as new kinds of vegetation spread across the world, fragmenting landscapes, small populations that could not refill their own ranks fast enough. No single blow, but a slow tightening of every margin that gigantism had always depended on. The bargain that built the giants was never unbreakable. It only worked as long as the world stayed within the narrow band the giants could tolerate. Think back, then, across the whole arc you have followed. It runs from small creatures no heavier than a large dog, through the invention of fast, unbroken growth and air-filled bones, through the long neck that fed a body without moving it, up to the 100-ton titans of Patagonia and the buried colonies at Auca Mahuevo. Every step was a solution that opened the door to the next, and every solution carried, folded inside it, the same quiet limit. A body can only grow so large before the ground, the plants, the blood, and the slow arithmetic of breeding all begin to push back at once. Stand one last time on that Nukan floodplain in the low light of a dry season evening. The nesting fields lie quiet, the scraped hollows filling slowly with wind-blown silt. Somewhere out on the plain, a great herd moves, tracking the last green along a shrinking river. The blade-toothed hunters shadow them at a distance, waiting for the old and the young to fall behind. It is a world in perfect precarious balance, a balance that took 100 million years to build and would not, in the end, hold. Stay low for a moment, down where the light has not yet reached. The floodplain around you is still grey with the last of the night, and the mud beneath your hands has dried into a mosaic of curled plates, each one cracked from its neighbour by weeks without rain. This is Patagonia in the middle of the Cretaceous, roughly 96 million years ago, an inland basin cut by a seasonal river that has shrunk back into a thin brown channel. The heat is already climbing. It rises off the cracked flats the way warmth lifts off skin, faint and steady, a breath the ground gives back to the sky. Above you stands the reason you came here. A titanosaur, one of the giants the Sauroposeidon ground would later remember, close kin to the animal called Patagotitan. From where you crouch, the nearest foreleg is a column of muscle and hide taller than you could reach standing. The whole animal runs perhaps 120 feet from nose to tail tip. Its weight is hard to hold in the mind, somewhere near 150,000 pounds. A living thing heavier than a loaded truck and longer than the river is wide here. For now it does nothing dramatic. It breathes. You can watch the great barrel of its ribcage swell and settle, slow as a tide, and each breath moves through a body built more of air than you would guess. The neck above you is not a solid mast. Inside those vertebrae runs a honeycomb of hollow chambers, air spaces threaded off the lungs, so that the bone weighs a fraction of what its size suggests. That is the quiet trick of the whole design. The animal carries a neck longer than most trees are tall, and it carries it cheaply. The sun clears the eastern rim of the basin, and the light comes flat across the mud. Now you can see colour returning, the dull rust of the dried clay, the grey-green of a low scrub that clings to the wetter seams near the channel. The titanosaur begins to feed. It does not walk to the plants, it reaches for them. Watch the neck sweep. It moves in a long, unhurried arc, the head at its tip no larger than a horse's, swinging across a wide field of low foliage while the great body stands almost still. This is the economy the whole lineage was built around. To move 150,000 pounds, even a few steps, costs an enormous amount of energy. To move a small head on a long neck costs almost nothing, so the animal plants its feet, and it harvests a half circle of the world without shifting its weight, mowing the arc bare before it takes a single stride. Come closer to the head as it works, and notice what is missing. There is no chewing. The teeth are simple pegs, narrow and blunt, crowded toward the front of the jaw like a row of pale dowels. They are not made for grinding. They strip. The animal closes its jaws over a spray of foliage, tips its head, and rakes backward, and the leaves and soft stems tear free and go down whole. You hear the tearing, the wet snap of a stem parting, the soft rush of swallowing, then quiet. Where a herd of grazing mammals would fill the dawn with the endless side-to-side grind of molars, here there is only that stripping sound and then a silence, over and over, a rhythm with a hole in the middle of it. The work of breaking down that food happens far out of sight, deep in the vast gut, where microbes ferment the swallowed greenery slowly over days. The animal is, in a sense, a walking vat. It gathers fuel with a small mouth at the end of a long arm, and it processes that fuel in a chamber the size of a room. Nothing about the head needs to be heavy or strong. That is why the head could stay small, and why the neck could stay long, and why the two together could reach so far for so little cost. The ark empties. The Titanosaur has stripped everything within its standing reach, and now it must do the expensive thing. It must move. Stand back for this. A stride begins not with a sound, but with a change in the ground. Before you hear anything, you feel it, a low tremor coming up through the cracked mud and into the soles of your feet, arriving ahead of the noise the way the pressure of a far storm reaches you before the thunder. Then the leg swings. The forefoot rises, a broad column ending in a pad the size of a low table, and it comes down into the softer silt near the channel with a slow, deliberate weight. Where the ground was wet from the shrinking river, the foot sinks. The silt closes around it and holds, and when the animal lifts away, the mud releases with a thick, sucking pull, a sound like something reluctant to let go. Each footfall presses a deep, sharp-edged basin into the sediment. Each one, in the flat morning light, holds a small pool of shadow, a dark print stamped into the silt and left behind as the animal walks on. Those pressed shadows are the only mark it leaves, and in some places, buried gently enough, prints like these would still be waiting to be read many millions of years later. The pace is almost impossibly slow to your eye. A single step can take a full second to complete. The leg swinging through its long arc, the body rocking gently over the planted feet. There is no hurry in any of it. A creature this size has few reasons to rush, and rushing would cost more than it could ever be worth. So it moves the way weather moves, gradually, inevitably, the whole living tower of it gliding across the basin one deliberate footfall at a time. Now turn your attention to the far edge of the flats, where the scrub thickens toward the higher ground. Something is there. It has been there for a while, keeping its distance matching the Titanosaur's slow drift across the basin without ever closing the gap. It is a predator, one of the great flesh-eaters of this land. A carcharodontosaurid built along the lines of the hunters this ground also held, kin to Maposaurus and to Giganotosaurus. Even at a distance you can read its shape. The long head, the narrow blade of the body, the balanced tail held level as it walks. Against the giant it looks almost slight. Against you it would be a wall of teeth. It does not attack, it shadows. It drifts along the same line, keeping to the scrub, its head low and level, watching the way a thing watches something too large to take on lightly. Whether it is truly hunting or simply passing through the same country toward the same shrinking water, you cannot know from here, and it would be a mistake to decide. What you can see is only the space held between them, the careful distance, two animals moving across the same flat under the climbing sun, neither one changing its pace for the other. The Titanosaur registers the shape. You can tell by the smallest things, the way the head lifts a little higher on its long neck, the way the sweep of feeding pauses and the great body turns a slow degree to keep the watcher in view. Then it goes back to browsing. At this size, a single healthy adult has little to fear from a lone hunter, and it seems to know the arithmetic of its own weight. The predator drifts on and eventually thins into the heat shimmer at the basin's edge, and the flats are quiet again, but for the tearing of leaves and the soft fall of enormous feet. The day burns on. The sun climbs to the top of the sky and the cracked mud grows too hot to touch, the air over it bending and rippling so that the far scrub seems to float. Through the worst of the heat, the animal slows further, feeding less, standing more, letting the vast furnace of its body idle in the warmth. The neck lowers. The great sides rise and fall. Around it the basin holds its breath, dry and bright and still, and the only motion for a long while is the slow swing of that head, reaching now and then for one more mouthful. Then the light begins to lean. The sun slides toward the western rim, and the flat glare softens into a long gold that stretches every shadow out across the mud. The heat that rose off the cracked flats all morning begins at last to ebb, drawn back up into a cooling sky. The colours deepen. The rust of the clay goes to bronze, the scrub to a darker green, the pressed shadows in the old footprints lengthening until they run together into bands of blue across the silt. The Titanosaur stops feeding. It has taken in through the long hours as much greenery as a small tree could grow in a season, all of it gathered by that reaching arm and now working slowly in the dark of its gut. As the warmth fades from the ground, it folds itself down toward rest, the immense legs settling, the long neck curving in, the great body lowering by degrees until it lies half-couched on the cooling flats like a hill that has chosen for the night to sit still. Its breathing slows, the basin darkens around it, and for this one animal, on this one evening, the day closes the way 10,000 days before it had closed, quietly, without event, a giant at rest under a reddening sky, while the river ran thin and the mud held the shape of its passing. In the end, no lineage could carry that much weight forever, and the giants settled back into the rock that had recorded them. In the end, no lineage could carry that much weight forever, and the giants settled back into the rock that had recorded them. In the end, no lineage could carry that much weight forever, and the giants settled back into the rock that had recorded them. So let the view come to rest now, low against the Patagonian ground, on a single thigh bone. It lies half in shadow, half in the thin morning light. 8 feet of fossil femur, longer than a tall person laid flat in the dust. Run your eye along it slowly. The surface has gone the colour of old iron and dry clay. This one bone once braced a corner of a body near 70 tons. Now it simply rests. You have followed these animals a long way to reach this stillness. Stay with the bone a moment. The weight it carried is gone, poured out into 10 million seasons of rain. What is left is the shape of a knee, the wide cup of a hip, the honest logic of a leg built like a pillar. Think back, without hurrying, on how such a leg came to exist. It began small. The first sauropod ancestors walked upright on 2 feet, no larger than many creatures you might meet in a field today. From those modest beginnings, one lineage crossed a threshold no land animal has matched before or since. The secret started inside the bone you're looking at. Sauropods grew fast and grew without pause, from hatchling to giant, laying down dense tissue threaded with blood vessels in an unbroken rush. There were no long stalls, no waiting for a gentler year. A body the size of a house was raised in a single accelerating lifetime. That headlong growth was the first quiet engine of their size, running steadily under the skin. The second engine was lighter still. Look closer at the vertebrae scattered near the femur. They are not solid. Air once threaded through them, carried from a bird-like system of lungs and sacs, hollowing the bone into a honeycomb of chambers. In places the neck bones were more air than material, closer to the light struts of a crane than to the dense marrow of your own arm. One neck bone from these southern giants ran a full yard across, wide as a dinner table, yet mostly empty inside. Breath, in the most literal way, was woven through the skeleton, and the neck was the masterpiece. Held out over the floodplain, it became a harvesting arm that swept across whole stands of fern and conifer, while the great body barely moved. A single sauropod could stand in one place and strip a wide arc of green, saving the enormous cost of hauling 70 tons from meal to meal. The teeth did no chewing. They were pegs for stripping leaves, and the plants went down whole, to be broken slowly in a vast fermenting gut. That is the story of how a small head could feed a mountain of an animal. There was a price written into all of it, and you can feel it if you imagine the head lifted high. To raise a skull 40 feet above the ground, the heart had to push blood up against the long pull of gravity at a pressure near the very ceiling a living body can sustain. Some sauropods carried their heads lower, and how high each truly reached is still gently argued over. But at the tallest extreme, these animals were living close to a hard physical limit, a great heart labouring near the edge of what blood and vessel could bear. Now let the view begin to lift. The femur shrinks to a pale line in the dust. The scattered bone bed gathers into a single quiet patch of ground. Around it the whole floodplain opens out, the seasonal channels, the cracked clay flats, the soft flooded silt where footprints once filled with water. Herds crossed here. Nests were scraped into these plains in their hundreds, shallow pits rimmed with earth, clutches of round eggs waiting in the warm sediment. Giants were born small and grew toward the sky along this very ground. Higher still, and the basin narrows. The floodplain that once ran to the horizon shrinks until you could cover it with a coin held at arm's length. The rivers become threads. The herds become memory, trackways that ran for hundreds of feet close to nothing more than a faint stitch across the land. And the layers of rock begin to stack in your mind, one age pressed onto the next, 70 tons of living animal pressed thin at last into a seam of stone no thicker than your hand. Whole worlds fold down into quiet bands of rock. Between that warm Patagonian world and this one lie about 100 million years. That is the gap the light has crossed to bring you a single femur in the soil. The animals that walked here are not going to return. Their kind rose, held the record for the largest creatures ever to stand on land, and then their line thinned and passed, the way every line must one day fade away. Take one slow deep breath and let that distance settle. It is not a loss to fear. It is a long, calm perspective to rest inside. So let the giants lie where they fell. Let Patagotitan settle back into its bone bed, several great bodies gathered in the same patch of ancient ground. Let Argentinosaurus keep its handful of vast vertebrae, and Dreadnoughtus keep its long, articulated tail curled in the southern rock. They ask nothing of the future, and they need nothing now. The floodplain that held them has itself turned to stone, and the stone remembers what the flesh could not keep. There is a deep peace in a thing so fully finished, so gently laid down. Let the view rise one last time, until Patagonia is only a curve of pale land, and the curve becomes part of a slow blue world turning quietly in the dark. The giants are down there still, folded into their seams, and they will keep for as long as the rock keeps. You do not have to hold any of it tonight. Let the numbers loosen. Let the long necks and the labouring hearts and the hollow air-filled bones drift and slowly fade away into the dark behind your eyes. You have come a very long way through deep time to arrive at this simple quiet, and you have earned every mile of it. Sleep well tonight, traveller. Good night.